Good morning, everybody. Welcome to this morning session. It is my great pleasure to introduce Alessio Figalli, who will talk about regularity of optimal transport map. Thanks, guys.
Okay. So again, thank you, Andrea. Thanks to the organizer for the invitation. It's always a big pleasure for me to be back in Pisa. I always say it's my second home, and also many memories in this room and in these corridors all around. So today I would like to give a kind of first an overview talk about regularity of optimal transport maps, and then present some new results toward the end. Maybe I will just start briefly to set up the problem. The optimal transport problem, we know what it is, but it's the usual picture. I will focus on a REN. So my ambient space is a REN and REN, and I have two measures, mu and nu, probabilities. And for simplicity, for most of the results of optimal transport maps, are specific to the quadratic cost. So I will discuss that essentially during the talk. If I have time towards the end, I will briefly mention something for more general costs, but I prefer to focus on the quadratic cost. So C of xy, which is our cost to transport particles, from x to y, is quadratic cost, so x minus y squared, let's say over 2. And we have a classical, beautiful existence and uniqueness theorem. So the two key players about this are here in this room. So first, Jan Brenier, and then Robert McCann. What they proved is that for the quadratic cost, if you give me two probability densities, then provided if mu of sigma is 0 for every sigma m minus 1 dimensional hypersurface, Lipschitz hypersurface, then there exists a unique optima T. Also, T is equal to the gradient of phi mu almost everywhere, where phi from Rn into R is convex. Right, so the usual theorem by Jan Brenier, it was stated for absolutely continuous measures, and usually requires some moments condition. In particular, you need like finite second moments, or in general, you need at least finite transportation cost. So you need to know that the cost to transport mu to nu is finite. Robert McCann generalized it, removing this kind of moment condition, so you can still prove this existence and uniqueness without even knowing that the cost is finite. And he stated slightly differently on the upper surface. It was something like finite n minus 1. It should give 0 measure to sets of finite n minus 1 dimensional measure. But in reality, what you need in the proof is that you don't see n minus 1 dimensional Lipschitz hypersurface. So this is, let's say, the most general result you can prove is optimal, essentially, in terms of assumptions. And we have this beautiful theorem that provides us with these optimal maps. And why optimal maps are beautiful? Just knowing that they exist and unique, and they exist and they are unique, it's nice in several applications. But for many things over the years, I think what made optimal transport maps so powerful is really that they have a structure. So it's not just a map; it's the gradient of a convex function, and this gives a lot of beautiful properties that I will not have too much time to discuss today, actually. But many of the consequences of optimal transport theory come really because T is the gradient of a convex function. So let's say I have this map, and then I could ask the most natural PD question that one could think of is assume that I have nice assumptions on mu and nu, like they're smooth, they're nice, I don't know, positive where they need to be positive, whatever. What can I say about the transport map? Does transport map inherit regularity from the densities. So there is a regularity question. And how do you address this? So I will do first a formal argument. Which is the following. So I'm going to assume that mu is f dx. So it means that it has a density with respect to the back measure. And mu is g dy. So g is the density of mu. And I'm going to also assume that t is a smooth differ. Okay? So I can do all the change of variables I want. Then what I have that for every function psi, I have the transport condition. So what is the transport condition? The transport condition tells me that for every test function psi, integral of psi composed with t d mu is equal to integral of psi d nu. This is the definition of being a transport map. Now let's rewrite the terms. So on the one end, this is the integral of psi composed with t f dx, and this is the integral of psi of y g of y dy. And now here I can use that t is a differ, so I can use t as a change of variable. I set y equal to dx, so y is t of x. Then you get integral of psi of t of x, g of t of x, then the Jacobian determinant, so that grad t dx. And then you compare these two expressions. So you know that this integral is equal to this integral. And this must be true for every test function psi. But psi is arbitrary and t is a diffeomorphism. So psi composed with t here, in reality, is any test function. I can generate all the test functions. And I have psi composed with t here, psi composed with t here. So if these two integrals have to be the same, what I will deduce is that these two terms must be the same. So I will deduce that determinant of gradient of t is equal to f over g composed with t. So this is the, let's say, the differential way of saying that t is a transport map. So t is a transport map if you have enough smoothness, this is equivalent to write this first order PDE. You see it's a PDE of first order on the transport map. But now Brenier and McCann comes into play and they tell me, no, wait, t is not any map, it's the gradient of a convex function. So I can substitute inside. So t is the gradient of phi, then the gradient of t becomes the Hessian of phi. And then I can write this. And notice that I can remove the modulus here. So before I had the modulus, but now phi is convex. So this is a non-negative definite matrix. So the determinant is positive. And I have a very nice PDE. Well, you can decide if it's nice or not, but I have a PDE. And this is called Monge-Ampere equation. And this is actually an elliptic PDE, so like the Laplacian, just is degenerate. So it's not uniformly elliptic. It doesn't have the nice regularity theory of the Laplacian. And in fact, there will be many problems to discuss regularity. So let's focus now on this equation. I will keep on with this. So when you work with PDEs, you have always a PDE and a boundary condition. So I don't know, when you study Laplace equation, is Laplace equals something in a domain plus Dirichlet boundary conditions. For instance, you prescribe the value of your function on the boundary, or maybe Neumann boundary condition. You prescribe the flux on the boundary. So there are always boundary conditions. But in reality, elliptic PDEs have interior regularity, which means that no matter what boundary condition you give me, if you're just interested in what happens inside your domain, you forget about what happens near the boundary. If you have a bounded harmonic function, the bounded harmonic function is analytic. So elliptic PDEs usually give regularization no matter what the boundary conditions are. Then the boundary conditions are usually just required so that you have global estimates. If you want estimates that go all the way to the boundary, then it's important that you have boundary assumption. Now, you could ask yourself, okay, what can I do here at this level? And for Monge-Ampère, there is a famous example by Pogorelov. So this is an equation which has been studied for many, many years. And in the 60s, Pogorelov noticed that even essentially if you solve determinant of d squared phi identically to 1, phi doesn't need to be C2. And actually, if you refine a bit Pogorelov, that phi doesn't need to be even C1. So, you can take the nicest possible right-hand side you can think of, like 1, a positive nice constant, and you cannot prove any local regularity. Okay? What is the reason? Is because I told you this is a degenerate equation. It cannot have regularity only coming from the interior. You need the boundary to play a role. So every time you try to prove regularity for this equation, you need to exploit what happens up to at the boundary. The boundary is what allows you to propagate the regularity inside. Okay. I will come back to this later, but in a sense, this is the rough philosophy. So what about now in our setting? So for optimal transport, what do I know? I know that the determinant of d squared phi is equal to f over g composed with grad phi. So if f and g are nice, this will give me, let's say, a nice PDE. Where is this equation satisfied? Well, let's say that f is supported in some domain omega, and g is supported in a domain omega prime. Then I have my map, grad phi here. So my PDE will be true in omega, right? Because this is an equation that lives here in this domain. But then what about the boundary conditions? So the boundary conditions are a bit bizarre, perhaps, because essentially the boundary condition is something like saying that the gradient of phi, the image of omega through the gradient phi is equal to omega prime. Okay? That looks a bit bizarre. There is a more canonical PDE way to write this. The way you could write this second equation here is the following. You fix, let's say, some function, I don't know now, capital G from Rn into R such that the set G equals 0 is equal to the boundary of omega prime. And then you say that G of gradient of phi is equal to 0 on the boundary of omega. So this is like saying that the boundary goes to the boundary. Okay? So this will be like, you see, a nonlinear version of Neumann. So it's some condition on the gradient. So Neumann is usually some gradient times the normal equals 0. Here I'm saying G composed with the gradient equals 0 on the boundary. So there is a way to write it also, a boundary condition. And then essentially you would like to exploit these two conditions, so the PDE plus the boundary condition, to get regularity. And the hope would be to say, if I take nice data, so let's say very nice F and G, very nice domains omega prime, then I would like to get smoothness. So from now on, omega prime are always going to be omega the support of F, omega prime the support of G. Okay. This is a nice hope. And then for many years, there was essentially no result about the optimal transport problem. There were many results about Monge-Ampère, but not for these boundary conditions. And then in the 91, essentially, but from 89, but really the first result of optimal transport was 91, and then many more followed. Luis Caffarelli came into play. He decided to attack this problem. When Luis decided to attack a problem, then usually solves it. That's how it works. And then he said, okay, let me ask about what can I do in this case. And he immediately noticed, well, there are problems to prove regularity, because consider this example. This is my omega. This is my omega prime. It's just the union of two half balls. I'm going to take F equal 1 here, G equal 1 here. Let's say this is like my E1 axis. This is E2. So here is the origin, let's say. And this is length 1, this is length 1. And what is the optimal transport? Well, it's not difficult to guess. You just cut this ball in two, and then the upper part of the ball goes here, and the upper part of the ball goes here by translation. You just translate the two balls. So the map T of x will be something like x plus something that splits in two. I don't know, something like sine of x2 times e2. So it moves up in the, if x2 is positive, you move up by 1 in the e2 direction. If x2 is negative, you move down. And this is the gradient of a convex function. Phi of x is x squared over 2 plus modulus of x2, which is a nice convex function, but you see it's not differential. Here you could say, well, okay, I knew this already, that you couldn't do it because you are trying to send a set which is omega, which is connected, into a set which is disconnected. So just basic topology tells me that you cannot have the image of a connected set is connected, right? So I cannot do, it's clear that I couldn't find a smooth map. And then, okay, then maybe connectedness is the key. But, you know, Luis, when he made this example, he also noticed that, okay, but in reality, you could take the same example and then put a very tiny bridge in between, length epsilon. You just put, again, uniform densities here, 1 and 1, let's say. Okay, maybe you need to normalize slightly the volume now that you added a small bridge. And what will happen, you see here that there was a line of discontinuity here in between, this line of discontinuity where the map really jumped. And what will happen now is that you will still have discontinuities kind of here and here. So in reality, what is here will go here, and what is here will go here. So maybe now you have still is connected. So here you see the line of discontinuities are two segments which are disjoint. So you have a way to pass through, but the map is not C1. So T epsilon is not continuous, or phi epsilon is not C1. Okay, but these are again the best densities you can think of. Okay, so then what Luis noticed is that there was a way for him to prove something, and the right assumption, and this was the theorem that Caffarelli proved in 91, is that if omega and omega prime are bounded domains, and then let's say f and g are comparable to 1, what do I mean by this? I mean that there are positive constants, little lambda and capital lambda, such that f is between little lambda and capital lambda in omega, g is between little lambda and capital 1 and in omega prime. So inside their support, where they are supported, they are bounded away from 0 to infinity. And key assumption, omega prime now is convex. Then you have the following thing: phi, the map phi is strictly convex. So, and C1 alpha. So phi strictly convex corresponds to say that the gradient of phi, which is the transport map, is injective. And C1 alpha corresponds to say that T is order continuous. Right? So just to remind you, right? Strictly convex function means like this. It has no flat parts. So convex, I mean, no strictly convex would be that your function has, you know, some part where it's affine, and strictly convex means, you know, if you take any linear function that touches, it only touches at one point. And once you have this, then if f and g are infinity, then phi is infinity. So in some sense, once you have strictly convexity, and in fact, strictly convexity is enough, but let's say strictly convexity of order continuity, in reality, then you can start to get smoothness. So in some sense, these were the two key ingredients, and here there is no optimal transport anymore. Here is just regularity for Monchampère. So it is really a pure PD regularity theory. Okay, so there is the first part where you need to use the boundary conditions to inherit something. And the way you use boundary condition is to prove this strict convexity of your solution. But once phi is strictly convex, the boundary doesn't play a role anymore. And at that moment, you can go on and you get all the regularity you can from just PD theory. This was well known way before by many results on the Monge-Ampère, especially by Pogorelov. There was a result by Trudinger and many others. But let's say it was very well known that the key is always strict convexity. So if your function is degenerate, there are problems. And it's clear that there are problems, right? Because what does it mean not to be strictly convex? Imagine just to give you why strict convexity is crucial, right? Imagine the PD determinant d square phi equal 1 formally. So if you're strictly convex, if you're not strictly convex, it means that you have a region where phi is, let's say, 0 on a line, on a segment. Okay, there is a segment sigma where phi is 0. But then this means that if I take in the direction of the segment, let's say E, dE of phi is 0 in that direction. But the determinant has to be 1, which means that in some other direction, the action should be infinity. So if I am formally into D, I take another vector E prime, then if this is 0, but I know that let's say in 2D, the product of the eigenvalues is 1, it has to be 0 times infinity to get 1. Right? So then dE prime of phi should be infinity for some E prime orthogonal to E. So you see, the only way you can solve, in some weak sense, a PD like determinant of the action equal 1 and being not strictly convex means that you have some singularity in some direction. In fact, the example of Pogorelov is of this form. When he wrote this example in the 60s, it was really a C1 function. In this case, it was a C1 function. You can make it even Lipschitz, as I say, which is not strictly convex in one direction. It's 0 along a segment, and then it has some singularities in the opposite direction, and sometimes these singularities compensate. In fact, the example is valid only in dimension 3 and higher, because in fact in dimension 2 you can prove that this cannot happen. So in dimension 2 is always special. Okay. Now I'm a bit cheating and not entering into 2 versus 3 versus higher dimension, but the key thing is this, right? So if you expect regularity, you expect the function to be nice and uniformly convex, because that's the only way the product of eigenvalues can be of order 1. Okay, so the key assumption, you see Caffarelli identified it, is omega prime convex. And then you can ask yourself, okay, why convexity? Why so important? So why omega prime convex? Why do you need it? The reason is this. So if you give me just one line, let's say 1 minute review of convex analysis. So if you give me a convex function phi, at each point, a convex function has some subdifferential. So what is the subdifferential of phi at x? Is the set of p such that phi of z is greater or equal than phi of x plus p z minus x for every z. So p is the set of slopes of all affine functions that you can put a touch from below. So for instance, if your function is not the one I drew, but maybe it's like this, it has a corner, then you have many possible lines that touch, and so the subdifferential is large, it's not 1 point. And so this is the subdifferential at some point, and then subdifferential of a set is simply the union of the subdifferentials. And what can you prove? There is a lemma, not too difficult to prove, lemma 1, let's say, for every E Borel, if mu and nu are absolutely continuous with respect to Lebesgue. So I'm trying to, this is a real lemma, it's not formal. So if I have two measures and they're absolutely continuous with respect to Lebesgue, phi, so T, the transport map T is grad phi, then mu of E is equal to nu of the subdifferential of phi at E. Okay? So this is kind of a transport condition, but it's not the usual push-forward condition. So the push-forward condition is different. So push-forward, so the transport condition, T being a transport, means that mu of t minus 1 of A equal nu of A for every A. You see there is an inverse map. And then here instead, I'm putting the transport on the other side and using the subdifferential. But here you can prove that is true. But you need some absolute continuity, otherwise it's false. Okay? So this has nothing to do with convexity. It's always true. Okay? It's just a different property of transport maps. But now, the reason why you need convexity is the second one. Let me do it. Well, lemma 2 is that if E is contained in omega and omega prime is convex, then the subdifferential of E is contained in omega prime. And so you see that now this is extremely useful. Why? Because this means that if I take omega here, and now omega prime is convex, and I take a set here, E, the image through the subdifferential, not the gradient, but the subdifferential, will be a set contained in omega prime. And then I know by lemma 1 that mu of E is equal to nu of subdifferential of phi of E. And if now mu and nu, so they are comparable to Lebesgue, so they are like F before, F and G were comparable to 1. So mu and nu are respectively like, so mu is equal to F dx and nu equal to G dy, where F and G are comparable to 1, like in Caffarelli theorem. Then you see that this is comparable up to constant to the volume of E, and this is comparable up to constant to the volume of the subdifferential of E. So now, in some sense, what I know is that the subdifferential of my transport map, of my potential, maps a set, every Borel set in omega into a Borel set in omega prime, preserving up to constant the Lebesgue volume, okay? But here I needed convexity, because the problem could be that if the target is not convex, like in my example of Caffarelli, the first example I gave, if you look at this line through the subdifferential is mapped into this square in my example of before, if you check. And here you see there is a set of zero measure, E, which is a line, a segment, which is mapped on set of positive Lebesgue measure. But here there is no measure. The nu is not there. My measure nu is supported here, but it doesn't see what's in between. So this equality is not true in this example because the target is not convex. Okay, so this is, you see, the crucial reason why Caffarelli asked for convexity. You may ask, okay, how much convexity will you need, right? Because you have convexity, it works, and then you have the other example by Caffarelli, which is very non-convex. It's two sets with a very tiny strip in between, right? So you could say, okay, but if I am almost convex, I take a convex set and I just reperturb it a bit. Perhaps I can prove something. Yes and no. Yes and no. So you can do actually bad examples. So Yash Javeri was a PhD student of mine. Studied this question, and in fact he noticed this nice example. If you take a square and now you put a dent into it. So F, let's say this is height 1. This is height 1/2. And the dent here is length epsilon. So your densities are as usual, right? Here is F and here is G. And you look at the map, T epsilon. Well, here T epsilon is never continuous. So even this small dent, no matter how short it is, it destroys continuity, okay? So this is really due to the fact that you are doing so you could think, okay, but here you're deforming my set in a kind of bad way, right? Because it's, you're putting corners. I mean, okay, here also are corners, but I could have smoothed it out, right? I could have made it very smooth. Let's say here the problem is happening around here and around here. Okay, there is a flat part, and then which is mapped to a set which has this inner non-convexity, like this corner inside pointing inward, and which is Lipschitz corner. So you could say, well, what if I make it smooth? So can I regularize? So what if the boundary was smooth? So here the second fact, so still that is in the paper by Yash, is that discontinuities they say discontinuity of transport maps, more than discontinuity. Discontinuity of OT is an open condition. So this means that if you take your domain omega epsilon prime, so and you consider omega epsilon delta prime, where these are smooth approximations of omega epsilon prime, and you consider the transport map T epsilon delta, so still from the square into these sets, which now are just a smoothed version of my set, then T epsilon delta is not continuous for delta less or equal than delta epsilon. So there is this, of course, delta will depend on epsilon, right? So the smaller epsilon, then the smaller has to be delta. There is a quantifier there. But in a sense, you can make a smoothed version of that and still not have smoothness of the transport map. So, okay, that's life, but it's good to know. There is also an openness in the other direction in reality. So if you have smoothness, then for smooth perturbation, you still have smoothness. So you could also do it in the other way. So there is open, it goes in both directions, but it's always the quantifiers that one needs to be careful about. So what is true by openness of continuity will be that if you give me delta first, so delta is like a smoothing parameter, for epsilon small enough, the transport map is smooth. So given epsilon, for delta small enough, the transport map is not continuous, but if you give me delta, which is like some smoothness parameter, then for epsilon small enough, you have smoothness. So there are these kind of dual results. But okay, here I'm trying to convince you that that convexity is important. And now the question that we investigated was how much boundedness of omega and omega prime is needed. I told you that the theorem by Caffarelli is for bounded domains. But in reality, for many applications, perhaps you have densities which are supported on the wall of space, like Gaussians, or Gaussian type density. And then you would say well, but I want to know that I can apply the Caffarelli, right? So if omega equal omega prime equal Rn, so if you have densities which are supported everywhere, in reality it's easy to generalize Caffarelli. So you take Caffarelli's proof, and essentially you see that it works. If everything is the whole space, both of them. I'm not sure I haven't found a proof written anywhere. So this, I think it was mostly folklore, in the sense that people always say it in papers, oh yeah, you just go to the proof and it works. I mean, there is nothing to and it's true. But then this could give you the wrong impression that, if just I remove boundedness, I could just say, oh yeah, and then you just repeat Caffarelli, it works. I must confess, I remember when I first discussed this a few years ago with Dario Cordero-Raskin, who is in Paris. At the beginning, I thought, yeah, it must be the same proof. Okay, so if I want to do it even for more general domains, even if they're not bounded, how much can it change, right? And then we started to discuss, yeah, what do? Do you repeat the proof? There is this step, there is this case, and then there is this last case, and then someone said, wait, how do you do that? So what is the difficulty when the target is not convex? In particular, the difficulty is when the target is not bounded. Omega is not really a problem. The problem is is omega prime. So of course, if you are in an unbounded domain, you have to think that your densities are like Gaussians. So they're not bounded away from 0 to infinity uniformly everywhere, because they have to be probabilities, but locally in each compact set, they're going to be between two constants. What is the difficulty? The difficulty is the following, that if there are, what you do in Caffarelli, it's very important for him to exploit the boundary condition. So the first thing he does is the following. Usually the transport map is defined only inside omega, but it's useful to extend it outside omega, to choose an extension of the potential phi. So what you do is that you say that, y omega prime bounded, what you do is the following. So you have your function phi, which is defined, let's say, from omega into R, a priori, canonically defined only in omega, my convex. And then I define phi bar of Z to be the sup over X in omega and P in the subdifferential of phi in X of phi of X plus P Z minus X. So what am I doing? I take a function, a convex function defined somewhere in some domain omega, and I say, okay, I look at all the plane that touch, they are defined everywhere, right? And then I just take the envelope of these planes, and this is my phi bar. So I just extend it as this is the lowest possible convex function that coincides with phi in omega and is convex everywhere in Rn. So now phi bar is defined everywhere. And now notice that, recall, if X is in omega, then we know that the subdifferential of phi of X is in omega prime, when omega prime is convex. And so this implies if omega prime is bounded, then my element P, the slope, P is bounded by a constant C for every P in subdifferential of phi of X, X in omega prime. So all these vectors P that appear here, they're all bounded, which means that my function phi bar, is Lipschitz, because all its tangent planes from below, they're all bounded, and these tangent planes are essentially the gradient of phi bar, so the gradient of phi bar is bounded. So this is a globally Lipschitz function. But now, if I didn't have the boundedness, this P is not bounded anymore, so it's not through this step. So here is the problem. So you don't have it. And what could happen for if omega prime is not bounded, what could happen is that phi bar is equal to plus infinity somewhere. So when you do your sup, your function, convex function, could become plus infinity in some regions. In particular, the case where it's very delicate is this, that what could happen is that your domain omega, let's say, is this, and then the region where phi is plus infinity is this, phi bar is equal to plus infinity is this, and you see in particular there are points on the boundary of my domain omega that touch the region where phi is plus infinity. So phi cannot be plus infinity inside omega because the gradient is going to omega prime, it's finite almost everywhere. But it could be plus infinity outside omega. And if the region phi bar equal plus infinity is on the boundary, then you see that here I have to be very careful what I do, because I told you that the regularity has to come from the boundary conditions. So it means that I need to go to the boundary of omega to get informations, but I have to work with a function that will have a jump, a very big jump. It could be finite and then plus infinity. So here is the difficulty, and then I will conclude now with stating the theorem. So we had the first paper with Cordero, Erascan, and myself in 19. And then very recently we wrote a preprint with Yash, where we proved that if, so, okay, I will state directly the final result with Yash. There was a previous result which was partial, but it covered already many cases. So if omega prime is convex, mu and nu give no mass to n-1 dimensional Lipschitz hypersurface. So we don't ask them to be absolutely continuous, we only ask them to give no mass. Plus, I will tell you what it is. Mu and nu are doubling. Then grad phi, grad phi is injective, so strictly convex, plus older. And then if mu is f dx, nu is g dy, f and g is infinity, then phi is infinity. You go on. But let's say to get to the basic step, which is, I told you, the key step of strictly convexity and all the regularity, you only need target convex, no assumption of boundedness, no assumption of boundedness omega, and you don't even need mu and nu to be absolutely continuous. You need both of them not to give mass to n-1 dimension upper surface, plus doubling. Okay, what does it mean, doubling? Doubling means that if you give me an ellipsoid, any ellipsoid E, and you take half of it, E over 2, then you want that mu of E is less or equal than a constant mu of E over 2, CR, let's say, for every ellipsoid containing a ball of radius R. So it's locally doubling. So if you take any ellipsoid in a, you want, this is important for small domains. So you have to imagine very, very tiny ellipsoids, and you want to know that your measure controls how the measure of alpha ellipsoid controls the big ones. You see that if mu is comparable to Lebesgue, this inequality is obvious, because the volume of E over 2 will be the same as volume of E up to a factor 2 to the n. And why doubling is nice? If the set is in BR, then no. So if I take ellipsoids which are containing all of them inside BR, right, then I'm asking the constant to be uniform. But everything has to be in BR, right? BR of 0. Yeah. Right, but this is true for every R, right? So I put it in this way. So, if you translate, then you have to use the different R, because you need to, if I translate, then I'm not containing BR, I will be containing B, a different radius, and then the constant can change. If the domain is bounded, then it could be a single constant, right? Then the doubling constant will be uniform inside my domain omega. And why doubling? Is the, I will say, so here is interior regularity. So yeah. But in reality, there was a boundary regularity paper, not for exactly this, but essentially this, so it was not in the unbounded case, but there was a boundary regularity paper last year by Yash with Ovidiu Savin, where they were doing exactly this case in the bounded set, but at the boundary. So the boundary regularity essentially is also done. So we didn't try to put everything together, but here I just focus on interior. But there is a boundary regularity. So why doubling? Doubling, essentially, what is the difference with respect to Lebesgue? It allows you to deal with density that can also vanish. So doubling doesn't require the density to be positive everywhere. For instance, you could take mu to be a polynomial P of x locally in a ball. P of x, the Lebesgue measure, where P is a non-negative and P is a polynomial. And this will be a doubling. Or you could take, if you are near the boundary, so what Yash and Ovidiu Savin did, last year, and then it was published this year, is that they treated the case, let's say this is boundary omega prime, and they treated the case of densities F and G, where F was like distance to the alpha and G was like distance to the beta, alpha and beta, non-negative. So the advantage of doubling is that it allows you to consider densities also that can vanish in some specific rate, and still you can get regularity of optimal maps. So I think I said everything I wanted to do. And okay, sorry, I'm probably a couple of minutes late, but thanks for your attention.
Thanks for this useful talk. Are there any questions? More questions? We started with some discussion. No? So I have one. So before stating this result, so you were mentioning this result by Javeri. Do you understand well that convexity is very important, but it's not then necessary, right? Because for the since you mentioned like that you have an openness condition for the regularity. Say if you perturb just slightly smoothly the square, you still get smoothness of the transport map. Is it correct or not? So
okay, what is true is that, let's say if you have a C1 regularity is not stable, but if you know that your solution, your transport map, so suppose that I give you two domains, even like degenerate, like squares, right? And I know that transport map between them in the region where I'm interested, let's say, is C2. Sorry, the map is C1, so the potential is C2, really. So classical solution, second order PD. Then if I perturb a bit the domain, the regularity will still be true. So I can even make them bend inside, and the C2 regularity will be preserved. So C2 regularity is locally an open condition. So the potential will be close to a function which is C2. And then there is kind of an epsilon regularity theorem that tells you that if you are epsilon close to a smooth guy, then in reality you're smooth.
So this applies also to some slightly non-convex domains, right?
Exactly. So if you bend a bit a slightly non-convex domain, you can... but you need to prove first that in the convex set, you have C2 regularity. And the problem is that usually for that, there are now results that avoid uniform convexity, very recent results. So if, let's say on the square, you have the problem of the corners that you need to smooth out, but it's not where the degeneracy happens here, right? So yeah, if you take a smooth version of the square, even if it is flat, you could do this and get smoothness.
And then another thing about the last part. This doubling condition in management is very much connected to Ricci quote lower bounds. So I know that say in the Riemannian setting, you have this other tensor which is related to regularity, but do you think that your result is saying that in the Riemannian setting also the Ricci quote lower bound can play some role for proving for regularity of transport, or this is a bit too far?
The point is that you need doubling for very small ellipsoids in reality, right? So the proof here is that you're interested in is sets which get smaller and smaller. So it's there is for proving regularity of optimal maps. So just to I reply, but I give also. So to prove regularity for general cost, there is an assumption on the cost which involves taking many derivatives up to 4, and then this builds some kind of tensor that you need from which you need to have assumption to prove regularity. Now doubling would be like just knowing how the measure mu behaves at small scales, and you see that it's more on mu than on the reference measure, because the reference measure will always be doubling at small scale. So it's I don't think here reaches the crucial point.
Okay. Any more questions?
Yeah, so if I understood correctly, the question is, can you do something for Dirichlet binary condition for Monchampère, right? Yeah, so this was like the classical theory of Monchampère. So when people studied it in the original papers, also by the first papers also by Caffarelli, were dealing with Dirichlet, right? So Caffarelli proved that if the boundary condition is nice enough on the domain, which is kind of like if you take for instance, if you take a smooth domain, like I think C3 uniformly convex, and you put smooth boundary conditions, Dirichlet boundary condition, then the solution is smooth. Again, because you inherit from the boundary the regularity. So if you want the classical theory of Monchampère was mostly developed first for Dirichlet, okay? And then here is a different boundary condition that people started to study. So I would say Dirichlet came even first.
But this is not exactly Neumann boundary condition, so it's a more global formulation of Neumann. So.
Yeah, right. Neumann is not so natural actually for this, right? So this is like the non-linear version of. I see it more as a non-linear version of Neumann, right? Because it's.
So is there a non-linear version of Dirichlet boundary conditions? Because this is.
But Dirichlet usually is already. Yeah, I see what you mean, but. I don't know. I mean, for Monchampère, what's natural is really the standard Dirichlet, right? Because you give me a convex function, you tell me what you do on the boundary, and you tell me what it does. Norman, it will be the flux. You would also do. I'm not sure how much it has been studied with the flux condition, right? Here, I think for most classical problems where you think about the applications of this, Monge-Ampère appears, for instance, when you prescribe Gaussian curvature, in addition to optimal transport. They were like a defined sphere problem in convex geometry that people studied, in affine geometry that people studied. And the natural thing was either first Dirichlet and now this, I think. I'm not sure people thought it. I mean, usually you look at the problem where it appears and then you ask yourself the PD question that is relevant.
Yeah. Just a curiosity.
Yeah.
You showed that in the unbounded case you can have problems, and in your example the set omega was not convex. I was just curious, if you add the convexity condition on omega, does it make everything simpler, or it's more or less the same?
It makes slightly simpler some proof because you don't need to worry too much about whether some segment is inside or not, but it doesn't change too much. So here you see the set phi equal plus infinity is a convex set, and could be that the boundary of omega, instead of being what it was, is something like a line, and then keeps going, and then they still touch, like in my example, right? So omega could be this. And then the set plus where phi bar is plus infinity is still some convex sets that touches omega. And so I would say it would be slightly different, but it's really a minor technicality. I would say the key, still the difficulty is there. So it doesn't help too much. Maybe just a last comment, if I can say now. If you remove all assumptions of convexity, there are regularity results that tell you, outside sets of measured zero, you still have smoothness. So there are still results if you remove convexity, but they're always then you have to remove singular sets here and there. So there is just for information. Giovanni.
Okay. Sorry. Could you go back to the doubling condition?
Okay. Yeah.
So if you put ellipsoid, I guess that what matters is that this must hold for ellipsoid which are not somehow round. So where one of the
axis is
axis. So what is it that matters? That one of the axes is large compared to all others?
All
so
cases.
Something like needles, or
all cases. You need
all cases.
All cases. Yeah. There is no. So when you apply this, is usually because you want to rule out. The proof of Caffarelli goes by contradiction. You assume that you have let's say, some set where your function is flat, so it's not strictly convex, and then you work around that region where your function is not strictly convex, and then that if your set was a segment, then your convex functions, if you look how it behaves, it will be like very elongated in one direction and growing very fast in the others, and this will be like an ellipsoid. This corresponds to an ellipsoid which is long in one direction and all the others are short. But then maybe if your convex function in 3D is flat on a two-dimensional piece, then it will be your ellipsoid will be very long in two directions and very short in three. So it really you need all of kind of ellipsoids for the proof.
Thanks.
Okay, any more questions or comments? Doesn't seem to be the case. So thank you very much, Alessio.
Thank you.
We continue this morning session with the second Alessio. So from Alessio Porretta from University of Vergata, we'll speak about optimal transport and mean field planning problems with entropic cost.
Okay, thank you. Thank you, and thanks to the organizers for the invitation. I'm very happy to be here and for the first time in this optimal transportation meetings. Okay, so I will talk about dynamical optimal transport. So somehow it's a slightly, complementary viewpoint. Okay, immediately after the first talk of today, I have to make precise that this is somehow a safe setting where omega is convex, it's bounded and smooth, but you may consider other situations, but the convexity is here. Okay, so what is the point in my talk is to consider essentially the classical, if you want, term in the optimal transportation, which is related, if you want, to the Wasserstein, to kinetic energy, plus an interaction cost. Interaction cost, which, I mean, is supposed to be increasing, so somehow this penalizes the concentrations. And you may think at power case, but maybe most interesting would be the case where you add just the entropy functional to the kinetic energy of the curve. Okay, so I mean, I cannot call it entropic optimal transport because this is reserved somehow to a different model. But it is another way if you want to add a little bit of entropy, but this is done along somehow the arc connecting two measures in the Wasserstein space. Of course, I mean, I'm not here being very precise, but you may give sense to that as you prefer. You may look at M as, say, V can be the metric derivative in the general framework developed by Ambrosio, Gigli, and Savary. Or you may switch from, if you want, from V into W and V, and then you consider, I mean, a couple of vector field and M. Okay, you could of course also be interested, and I understand, in epsilon small, but in my talk today, epsilon is essentially being 1, and the relative entropy will be taken with respect to diffuse measures in the form of exponential of -v, which is the simplest model. Okay, so I will first talk about the motivation and the connection. I mean, to be honest, my interest came from some infill gain models, and then well, it's somehow expected that this kind of interaction terms should bring regularity in, I mean, for the optimal curve M. So you expect that, and so somehow I think that what is interesting here is to go a little bit in search of ellipticity behind. We have seen that this is crucial even in the classical optimal transport through Monge-Ampère, but now you will see this coming from a different perspective, which is not related to Monge-Ampère. So how and where is it observed? And this will lead us to talk about quasi-linear elliptic problems and vanishing viscosity things. Okay, and this is strongly related to displacement convexity, because you may guess that an advantage of this kind of functionals is that they should be, and they will be, very robust in the sense of displacement convexity. Okay, so I will then somehow state some typical results, and then I will talk about, say, from classical to weak solutions. There is I mean, nowadays, I mean, this kind of models were introduced also, I mean, since now a decade at least. Essentially, they started as congestion models in fluid dynamics, traffic flows, as variants, if you want, of the Benamou-Brenier formulation. And in that context, M is the density of a large number of particles, and this kind of models were just observing, I mean, we're just trying to describe situations where M is transported according to the kinetic energy plus some interaction between particles or whatever. There are many contributions. I would probably have missed something, but specifically, I mean, in particular, Tazzo, Jimenez-Ude, and Giuseppe with Filippo worked a lot, and then Guillaume Carlier and Filippo worked a lot on that. So typically in these models, F is superlinear with respect to M, and this again should go in favor, of course, of say avoiding concentration effects. There are other models which I won't talk about, which are a bit related, but where somehow this penalization of the congested areas is observed, I mean, by penalizing the velocity. So I won't talk about that, but this is related. And it was also related to somehow the formation of geodesic in Wasserstein spaces. But they share some similarities, but okay, they are outside somehow the framework of my talk. I would like to mention, maybe this is less familiar for you, the relation with this mean field game theory. So this in midfield games, this is a theory initiated by Lastille and Lyons in 2006. The main difference is that the particles are rational agents. So they take decisions, they optimize some cost function. So you have a dynamic, which in this case is just maybe observing some trajectory with some velocity, and there is a value function for the generic agent, and this value function has some Lagrangian cost and possible some cost depending on what's happening around. I mean, for the viewpoint of the agents. And it's important here to notice that at least in what we call midfield games, in the concept of Nash equilibria, this is considered a priori as an exogenous family of measures, which is somehow supposed by the agents to be a certain repartition of the density. And then there is a Hamilton-Jacobi-Bellman equation, which is classical here, well, this is frozen if you want. And there is an optimal policy, and then, the dynamics, the optimal dynamics will be driven by this optimal policy, and the Nash equilibria is when, indeed, the law of the optimal trajectory coincides with the supposed rational anticipation of the agent. So this is a Nash equilibrium, or at least, it goes back to the concept of Nash equilibrium, and then this links the two equations into a system where there is a continuity equation. While you observe this HP is the derivative of the Hamiltonian function with respect to P, and then this is the Hamilton-Jacobi equation. Okay, of course, I will quite soon also skip to a very simple case where H is just a square function, but just to keep the setting as general. And I just want to mention that in this context, for this modeling, giving a final payoff for the agents would be very natural. While prescribing the two marginals for the M sounds like what is called in this context a planning problem. It's like a sort of policymaker would like, to bring the distribution of players from one configuration to a final target one, but knowing that the players are still optimizing along the times they are running cost. And so this is somehow can be seen as a sort of singular limit of the payoff problem, and I will come back to that later. Just to mention that, even if I'm not going to talk today on that, if you just take exactly the same setting, the same modeling, and you add some small or big noise, if you want, in the dynamics of the agents, then this, of course, the same kind of setting stands, and you simply observe coming a diffusion inside, and this is related to this Schrödinger transportation problem that was mentioned so many times in this conference. So somehow they belong to the same family of dynamical optimal control or optimal transport problems. Okay, so this is to say that I will concentrate mostly on the system of say the M trajectory and the U function. Well, if you take the primitive of this F function here, then you may just, if you want to make the link with your functional in optimal transport, this is just the optimal, say, couple, and this is the velocity, you see, which comes from the Hamilton-Jacobi equation, and this is, you may interpret UM as the state, adjoint state of the control problem, or if you want, this is HP of the U is the velocity, the optimal velocity, which drives the optimal trajectory. In the classical optimal transportation, you don't have this term, and U of 0 and U of 1 are, or maybe minus U of 0, are the Kantorovich potentials. They are defined indeed through the optical formula of Hamilton-Jacobi in classical optimal transportation. Just a remark, I will somehow understate a little bit that the problem is convex, provided big F is convex. And what I understate is the Benamou-Brenier trick, which is that switching from V into MV, this term becomes convex in the couple MW, and if this is convex in M, so that there is convexity behind. Just to mention a little bit, in Mifflin models, actually, U and M so represent a Nash equilibrium. This Nash equilibrium does not coincide with a global optimum. And okay, I'm not saying anything, but somehow this depends on the fact that M was frozen in the optimization of the player. So that's the concept of Nash equilibria. So there is what is called the price of anarchy in the gap in the optimal value of the functional at the Nash equilibria and in the optimal value of the functional in the optimal control problem. Okay, but this is a minor point, please. Sorry? Of flux, sorry. Of flux. Yeah, sure, sir. Okay, so okay, now let me go a little bit in search of ellipticity, and so this is an idea suggested by Pierre-Louis Lyons in the context of Mifflin games, exactly, by a way of using, if you want, the increasing character of this congestion term. So you see, you take the Hamilton-Jacobi, and if f is increasing, you may express m in terms of the u. And if you plug now this expression in the continuity equation, well, you get a second-order equation of u in the tx variable. So you see very well that m is a function of the first derivatives of u. So when you insert here, what you find, at least in a first computation, you find a divergence in tx, because you see that that's the divergence structure of the continuity equation, of a function which now couples all the first derivatives of u times space. You can expand this to see a little bit more this ellipticity, and you expand that into so now non-divergence form equation, which has a very nice structure. And you see it's in the form of the trace of A deviation of u, and this matrix A is the sum of two contributions. So one is only saying, if you wanted a velocity vector A0, this is a degenerate matrix, and this only sees the elliptic, so if you, sorry, the space variables of u, the space derivatives of u, and depends, as you see, from the convexity of the Hamiltonian and from this term. And this is an elliptic equation in a cylindrical d+1 domain. Okay, I will now give you, this computation for the simplest possible case when h is 1/2 gradient u square. So you can say that the coupled UM, so classically the system, if and only if M can be expressed, this is of course for F increasing, as will be in all my talk. And if and only if, so U is a solution of this degenerate elliptic equation where you have this somehow elliptic term weighted by the congestion function, and this part, which I will call the trace of A0 deviation, which, as you see, is somehow defined through the velocity vector du. So it's a quasi-linear problem, and there are, some interesting remarks on that. So first of all, prescribing the marginals on M leads to a nonlinear Neumann condition in time, in the time derivative. So that's a cylindrical domain. In this context, you may even think that the space domain is a compact. It's like in the torus. So the boundary condition here is for the time t equals 0 at the top of the cylinder and at the bottom of the cylinder. And this is a nonlinear Neumann condition, which is rephrasing the prescription of the marginals. And what's very important, what's very interesting is the entropic case. So if you take f like the logarithm of m, which is the derivative of the entropy, this precisely corresponds to an elliptic regularization of a degenerate problem. So it's really reminiscent of the vanishing viscosity approximation of degenerate problems, even if this is only in the space variables. And you also see very well also the role of the potential B. Okay, the equation is uniformly elliptic provided this term here is positive. Which is, of course, precisely the case with the log, but of course not only the log. Otherwise, the ellipticity will degenerate on the set where m is 0. So you see very clearly here that, of course, outside the support of m, there is this loss of uniform ellipticity. Okay, so what to do with this elliptic problem? Well, what was in the suggestion of Lyon's approach was to use it for, as you do for quasi-linear elliptic equation, to get gradient bounds for U. This is, I mean, quite classical. If you have a quasi-linear equation, even it dates back to the old and nice idea of the Bernstein method, which is essentially that convex functions of the gradient are subsolutions of an elliptic problem, and so they essentially take maximum on the boundary. And the Neumann condition may help in this respect. And this is the kind of estimate which was, already suggested in very special cases, or maybe in the courses of Pierre-Louis Lyons at Collège de France, but then in much more generality developed recently by Sebastian Muñoz, or at least for the periodic case. Okay, this is not maybe the most general version, but this is readable enough. So you take a classical solution of this equation with this Neumann condition, then there exists a constant such that you estimate that the gradient, this is time-space gradient, in terms of the L infinity norm of U. And the constant depends on the, say, f of m0, f of m1 in Lipschitz here norms, of course on the potential, and also on the upper bound of m. This can be relaxed, but okay, it's not important now. And of course, on the lower bound, this is the ellipticity. Okay, so I extended that to a convex domain with Neumann conditions, but the idea is there. So I want to discuss that, I mean, this kind of estimate is still depending, in particular, on the bounds of U here. And also, I mean, it is also depending somehow on the upper bound of M. So I would like now to discuss this issue, how you get those bounds. And this is where you find somehow some more ellipticity with respect to M. This was addressed in paper by Filippo with Ugo Lavenant, a very interesting paper, in my opinion, where they underline that these congestion terms could yield some local bounds on the density, so some local regularizing effect using, I mean, flow interchange techniques and geodesic properties of Wasserstein energy. So this somehow somehow suggests that what is behind is a role played by displacement convexity, an elliptic role somehow played by displacement convexity. And indeed, this is true. I mean, you can obtain, first of all, a quite general displacement convexity inequalities in this setting. This was first addressed by Diogo Gomes and Senecci in 2018. And then, okay, I mean, extended a bit by myself. Again, you assume that U and M is a classical solution of the system. And then, exactly as in the celebrated result by Robert McCann, you define your function P, which is U prime R minus U, and provided you have a certain inequality for P, you get a sort of convexity estimate on the norm. Somehow it's not a norm, or say the evaluation of U along the trajectory M of T. And in general, the typical effect of that is that you get global bounds on the density, in particular, for example, in LP norms, depending on the LP norms of initial and final density. That is typical application of displacement convexity, which here are obtained, so in what is called the Eulerian, if you want, approach. So directly, if you want to working on the system. But there is more than the global regularity, because somehow, if you really observe this kind of inequality, you notice very well quantitatively that there is still this ellipticity floating around in this inequality, which comes from the product of M f prime of n, which in particular allows to obtain the result by Lavenant and Santambrogio, maybe even slightly more general settings, assuming only that this quantity is now, say, perceived, or if you want positive, just for S large, because now you are just interested in situations where M is, you want to estimate its L infinity norm. And then you get this, if you want, L1, L infinity regularizing effect. And the constant here only depends on the Lipschitz norm of the potential. I will give you a proof for that because it's very simple. And so that's what I prefer without using a flow interchange, just using this displacement convexity, is that you start by this inequality. Okay, forget for the moment that the potential somehow will play a minor role so far. And so you use this inequality here, and then you simply use Sobolev inequality. You interpolate with the fact that your M is mass 1, and what you find here is a very nice superlinear behavior in terms of the power, say, m to the p, so the norm, if you want. So if you define your function, which is the integral of m to the p, well, this satisfies a very nice ODE. It's a subsolution with a superlinear power here. And it is exactly this superlinear character which tells you that there are barrier effects at the boundary, which means that the information at the boundary, is improved, doesn't really care, and you get this interior simply bound, if you want, by just comparison principle on that. So you see very, very elementary proof of this. Okay, I want to close somehow the discussion between these estimates, and then of course I will spend all these estimates to get somehow to put together the pieces of this puzzle. There is a step which is also relevant here to notice, which is how you get this bounds on U. In the final problem, well, U is invariant up to addition of a constant, you see from the system. So of course you need some normalization of U, and you need somehow to inherit this estimate from M to U. Okay, so of course this is now less obvious because you have this, say, coupling term in the Hamilton-Jacobi equation. So one way of doing that, which is very natural in the viewpoint of the dual optimal control functional, is to normalize U as zero average in terms of one of the two. Well, okay, I would prefer here to use the normalization in terms of the final marginal M1. So U hat as U with zero average in terms of M1. And then the first thing you get is this interior, say, bounds from above and below, which only depend on the sup norm of the potential and the sup norm of M. And they simply, are a consequence of the Hamilton-Jacobi inequality. These are local bounds, so this will be important when you want to relax a bit the assumption on the marginals, because you have this L1, L infinity regularizing effect, and now you have somehow this L infinity from N into local L infinity for U, so you see that everything starts to being consistent. But of course, in the first step, you also want global L infinity bounds for U, and the global L infinity bound depends on the marginal, and in particular on the f of M1. So here you must be careful, because if f is the logarithmic function, as in the entropy functional, having an estimate which depends on the log of the marginals means that you are assuming here the marginals being strictly positive. So somehow the global, in the case of the entropy term, the global L infinity bound depends on the strict positivity of the marginals, but not the local one, and this is, of course, important to stress. Okay, so let me now a little bit summarize this kind of approach. So the approach somehow uses this idea of transforming the problem into a quasi-linear elliptic equation, trying to find gradient bounds. The gradient bounds depend on the bounds itself on U and M, which you may take from other ingredients like displacement convexity and Hamilton-Jacobi somehow. Okay, so I will state here the result for the entropy case, which is maybe one of the most interesting in my viewpoint. So in this statement now, omega is convex, bounded, and smooth. And okay, the potential is sufficiently regular as it is necessary. And so far, I'm still requiring the marginals to be strictly positive on the whole of omega. Okay, then you can show that there exists a unique minimizer of the problem. Well, uniqueness comes from straight convexity. This is not. But the point is that the important fact here are that M is strictly positive everywhere in time and space. Is represented in this form as an exponential of this. This is simply coming from the Hamilton-Jacobi, if you want, where U is the unique, up to a constant, if you want, solution, classical solution of this quasi-linear elliptic problem, where you have this Laplacian, which actually the constant one comes from the constant one here. So U here, I mean, there are this Neumann condition. Okay, so sorry, there is an epsilon which has remained from other, say, but this is stick to 1 in this result. Okay, so this is a result of classical solution, and it's useful, very useful to have this result. For example, if you want to show properties in the limiting problems of optimal transport where you miss this kind of regularity, you can lift the problem at this level with a bit of entropy. You have, for example, all your displacement convexity inequalities in the Eulerian fully justified computations, and then many things are stable. So that's, in my opinion, also a very important approximation that you may use for other purposes. Let me just give you on the strategy here. So I want just to stress maybe one point in the strategy, which is that because of this invariance of U up to translation, it might be convenient, this might be just one idea, to start with a problem where the L-infinity norm of U is somehow stabilized, and you may replace your Neumann condition with a Robin type condition, adding a small parameter delta in the quasi-linear equation. Well, the existence for that is maybe one of the technical steps, because you require a theory of quasi-linear elliptic equations, because at this stage you have to use this continuity methods, which say that if you have Lipschitz bound and C1 alpha bounds, then you, with the continuity method, you can solve the quasi-linear elliptic equation. This dates back to the classics, I would say. But it's important to notice that this approximation, which is natural even in the elliptic viewpoint, is also very natural in the optimal control viewpoint, because this corresponds to penalizing the final payoff, or this case also U at time 0, for U. And you see here, somehow, this is a way of using the adjoint state to lead your distribution M towards the constraints, which are M0 and M1. In the viewpoint of, for example, of optimal midfield control, maybe it would be very natural to keep the initial distribution and to penalize the payoff in a way that these agents distribute as you wish in the end. Okay, so, and then the proof goes with the ingredients I told you. You use first the displacement convexity to show the bounds on M, then you deduce the bounds on U, which, as I said, here depend on this guy, and then it's important that once you have stabilized the L-infinity norm, you have access to the gradient bound of U, and it's a remark, I mean, it's important to remark the bound from below of M follows from the global gradient bound of U. I mean, we do not know somehow other ways. So this is the global gradient bound of U will give you a uniform bound from below for the density. And then, okay, U is Lipschitz, and then there is the elliptic regularity. U becomes C1 alpha and then classical. Okay, let me just sketch. The potential may have a role. So far I neglected that, but if you, of course, realize that the heart of this approach relies in gradient bounds. Well, the gradient bounds, they somehow are related to this Bernstein method, and probably many of you already have thought, well, okay, but the Bernstein method is essentially the Bochner formula in general terms, and then you expect the role of potential also to come around. And it is. Well, first of all, it can be used to get bounds on, if the potential is strictly convex, then you may get more easily some bounds on the gradient independent of the L-infinity norm, so it's an easier setting. And you can also get bounds on the density without going through the displacement convexity. And in particular, you may apply, for example, this for the same problem with the relative entropy compared to Gaussian-like measures in the whole space. Of course, the setting is very similar, except that the measure will be, say, bounded above and below by this, say, Gaussian-type weights. And then you get the unique minimizer, which also preserves kind of above and below bounds Gaussian type. And okay, so I only sketch here that there's work in progress with my PhD student Gabriele Bocchi, where, as you may expect, and I was a little bit mentioning, I mean, this kind of results can be extended to the setting, at least, I mean, of the Riemannian, smooth Riemannian manifold, and this estimates require either that the Ricci curvature is no negative, or what you expect that the Ricci plus the Hn of V is no negative. Essentially, this is inside the Bochner identity from my viewpoint, and this is the main same tool that you use in this kind of approach. Okay, now from classical to weak solutions. Well, of course, you would like to relax many things in this setting. You would like, for example, to, okay, first, you might be willing to relax the ellipticity. You might be willing to relax the positivity of marginals. And, okay, if you also want to change, say, cost function, you might be willing to change the Hamiltonian. And any of these kind of changes will destroy a bit the full ellipticity of this quasi-linear elliptic equation. So you need a setting of weak solutions, and fortunately this setting, I mean, is there since, I mean, the works on mean-field game theory, in particular Pierre Cardellaghe introduced these ideas, and then we worked on that also, and also Filippo used with Pierre this, and then recently, jointly with Carlo Rieri and Giuseppe Savare, we also revisited this kind of weak formulations more in the viewpoint of optimal transport. What is this notion of weak solution? Well, essentially, U is only required to be a sub-solution of the Hamilton-Jacobi equation, but the information that you are missing here, you expect to be fully preserved on the support of the measure. And the key idea behind that we developed with Giuseppe and Rieri is that essentially the sub-solutions of the Hamilton-Jacobi equation and the solutions of the continuity equation, they form a nice duality pairing in the sense that you are allowed, what you would formally would like to do is to multiply, I mean, to project, if you want, or to multiply by m this inequality, and this can be fully justified. And okay, this is the formal definition of solution of this weak solution. I won't insist on the details. Just let me stress that the equality on the support of M is, you may require it in a more, say distributional way, but in the end, it's enough just to have the equality of the, say, the optimal level of the functional, which is essentially the equality, as you might recognize, between the primal and dual optimization problems. Okay, the traces of U are well defined even for sub-solutions. This is what we developed by studying the properties of sub-solutions of the Hamilton-Jacobi in our paper. And then you can use the setting for stability purposes. So for example, I give you just two examples of that. So one is okay, you want to still attack the kinetic energy plus entropy function, but you want to remove the strict positivity of the measures. Okay, well, so for example, you are still in omega, but you want to use measures with compact support. So what you can do, of course, you can take positive smooth measures approximating your measures, then you get the smooth solutions I built before. And then, I mean, with this kind of, you get compactness. Well, the compactness is a little bit consequence of several of these ingredients, a little bit of this ellipticity in between, displacement, convexity, etc. And then you get the convergence to the unique weak solution according to the previous definition. You also can prove that the measure is strictly positive almost everywhere between 0 and 1, which says that this compact support is immediately lost. And this is another instance of this, say, regularizing effect. And then MDU would be a minimum in a suitable, maybe, formulation, as I maybe mentioned at the very beginning. Another kind of stability that you might be willing to exploit is, okay, now you want to consider other congestion terms, but you would like to have many nice estimates that you may add a little bit of entropy here. So this is another stability limit. In this case, this is still so far for F increasing. So say, this F convex or its derivative increasing. And then you use this smooth solutions we built, and then you can pass to the limit and converge to the unique weak solution. Okay, so I try not to gain a little bit of time for the coffee break. So I will just mention that there are many questions, in my opinion, that are around this kind of approach and the comparison with other properties and other, say, PDEs. I will just mention one, which I think might be interesting, which is actually a work in progress that we are doing with Pierre Cardelaguet and Sebastian Muñoz, which is related to, say, more detailed, possibly more detailed study of the qualitative behavior of this transportation of M from, say, 0 to 1. Because there are two regimes which now, I mean, quite clearly, it seems they appear in this kind of problems. One is the entropic regime, when F is the log, and then you see when M0 has compact support, then immediately you get positivity of M. And so somehow its behavior looks more like heat equation for M. You have L1, L infinity regularizing effect, then you have this gain of positivity, strong maximum principle, and then once you have that, you have smoothness because the problem behind, as I explained, has ellipticity. So it's really sort of heat equation. But then you have another regime, which is power type congestion cases, when you still have the L1, L infinity regularizing effect, but solutions, you lose the strong maximum principle somehow. There is a degenerate elliptic equation behind, and solutions are not smooth and may have compact support. So the behavior really looks like porous medium, and even more than this looks like. In fact, we found that there is a self-similar solution with compact support, for example, in this case, which, okay, takes this form. So maybe some of you can recognize that this is exactly a rescaling or in the family of the Barenblatt solution for porous medium. And okay, so this self-similar solution really shows many phenomena that now maybe would like to show for different marginals. First of all, the M is connecting here a direct mass. So this is concentration function at t equals 0. So this is a function which concentrates like the Barenblatt solution, and then it moves and propagates the support. So it's an instance connecting a direct mass with a compactly supported measure. And the propagation happens with finite speed of propagation. The M is only Hölder continuous and behaves, as I said, like the Barenblatt solution. So this opens, in my viewpoint, the very interesting question whether we can prove, of course, for general, say, marginals, or possibly, say, general marginals, some regularity of the free boundary, which in this context, of course, is a new problem. Okay, so I mean, I hope I regained something for the coffee break. So I thank you for the attention.
Thank you for the talk. Any questions, comments for Alessio?
It seems not. It seems not. But okay, so far, I mean, it seems not with the finite mass, with preservation of mass. But okay, there is something we still. In my opinion, maybe to some scale, it's possible that there is, but not directly for the problem as it is. Not yet, I should say.
More questions? Okay, so now let's thank Alessio again. And we resume at 11. Welcome back. It is my pleasure to introduce Filippo Santambrogio from Paris, who will talk about a survey of, no, sorry, from Lyon. Sorry. I didn't update myself. A survey, so we talk about a survey of energy estimates in diffusion PDEs that can be obtained mutatis mutandis in the corresponding JKO scheme.
Okay, thanks a lot. Thanks a lot for the introduction. Thanks a lot to the organizers for organizing again this meeting after some years. It's really a pleasure for me to be here, and it's really a pleasure to be in Pisa any time that I have the occasion. It's a beautiful city where I spent 7 years of my life, and I'm very happy to come back at every moment. Just a while to change the microphone. I'll try to use this. Okay. Yeah, it seems to work. So this very long title of my talk today is a way to summarize many topics that have been studied, very much intercorrelated with each other, that have been studied in the last years concerning the JKO scheme. So we know that one of the applications of optimal transport is the fact that you can study some evolution PDEs as gradient flows of some energies in the vast space. And really, from the very beginning, the idea by Jordan, Kinderer, and Otto was to have a time discretization of these and to study these PDEs as a limit of a sequence of optimization problems involving the vast distance. And one can ask many natural questions about this. In particular, one of these questions is which kind of behavior that we observe in the PDE can be observed in the JKO scheme, in particular for the PDEs that we already know. The most classical PDE which has been studied with the JKO scheme from the very beginning is the Fokker-Planck equation, or the heat equation. Of course, if you're able to say something about this PDE, then you hope also to be able to say something about more complicated PDEs for which we don't have yet results from the continuous setting, let's say studying the continuous in time PDE, and maybe we can obtain results using the JKO. And I'm also very glad to say that I was just informed yesterday that a project that they presented about these topics and related topics has been awarded an ERC grant. And it's something which arrived very late, but I've just been informed yesterday about this. So what I will be presenting, it's after a very short introduction about the JKO scheme, I will pass a review of some estimates, some inequalities, some asymptotic behavior that you can find in some very classical PDEs and that you can rediscover on the JKO scheme. So I will in particular consider what happens to integral functions, like what happens to the entropy, to the LP norm, or to some other quantities like integral of a function of the density or density plus something else along the evolution of the JKO scheme. Then I will consider L-infinity bounds in the sense of upper and lower bounds for the densities, upper bounds for the gradients, some bounds also on the second derivatives in some cases. And then I will move to integral quantities on the gradient, like what happens to the H1 norm, to the Fisher information, and so on. And I will just leave the last extra estimate, which is something new, and I will explain, for the end, I will explain why do I need some other quantities to be studied. So let us just very briefly recall what I'm speaking about. You take a function defined over probability measures, and the gradient flow will be this evolution PDE, which is the continuity equation with a vector velocity field, which is minus the gradient of the first variation of the function. The first variation is defined in this way, and the gradient of the first variation is what Pierre Cardier-Leguet used as a derivative, as a gradient in the Wassermann space for applications to another setting, to the master equation, and so on. The time discretization is, instead of solving a continuous in time PDE, you fix a starting point, you fix a time step tau, and you iteratively minimize the value of the function plus the distance squared to the previous point divided by 2 tau. And so you get a sequence. In this, so very often I will just be interested in the static problem. I give you a function g, which will be rho k, and then I look for the minimizer of these. So G is a density which is given. It will be a probability density, maybe with some regularity. You can, if you want, suppose that G is as smooth as you want, prove everything supposing that G is smooth, and then pass to the limit. But passing to the limit in each variational step, you don't have to pass the limit in evolution equation. Just pass to the limit a variational problem. So it's static. It's much easier than having a limit on an evolution equation. So I give G and I find the optimizer rho. What are the optimality conditions? The optimality condition, formally you can write that the first variation of the function f plus the first variation of the Western distance, which is the Kantorovich potential phi, divided by tau, should be constant. So the Kantorovich potential is the Kantorovich potential for 1/2 x minus y square. So the transport map is not grad phi. The transport map is identity minus grad phi. So it's x square over 2 minus phi, which is a convex function. And so it's identity minus Hessian of phi, which is positive. So this is not exactly the convex function that we saw as a potential in Alessio's talk. By the way, you can use this to formally guess why the equation that you find is the one that I presented, because if you take the gradient, grad phi is the difference between transport map and identity. So you have a t of x minus x over 2, which appears, which is a sort of discrete velocity, and you find why the discrete velocity is the opposite of the gradient of the first variation. Some examples. Most of what I will say will be in this case. The function is an integral of something depending on x and rho of x. Rho of x, I mean the density. So a function which is only defined for absolutely continuous measures. So for instance, suppose that f is superlinear for every x, so that this function is Lauer semi-continuous for the weak convergence of probability measures. And in this case, the df over the rho is just the derivative of f with respect to the variable over input rho. If you take f of x S to be the entropy plus a potential, you get the Fokker-Planck equation. If you take a certain coefficient times the power, you get the porous medium equation. You can have other variants where the, please, Robert. Yes, you're right. Yes, sorry. Yes. So that if you take the, yes. You take derivative with respect to S and you get the V. Sure, thanks. So in this way, this part of the energy is the potential energy, the integral with respect to rho of a given function. You can have other kind of spatial non-homogeneities in the sense that you can take f of s plus something, take f of s divided by something if you want to consider, for instance, a relative entropy to a reference measure or a relative power to a reference measure. For the entropy, if you take entropy of rho over m, it's essentially the same as taking entropy of rho plus something linear in rho. And you come back to this. It's not the case if you have a power. And the kind of question that we consider is this a typical example. For instance, on the heat equation, we know that you can differentiate in time the L2 norm and you get -2 the H1 norm. Can I get the same in the JKO? That is, the L2 norm at the next step is equal to the L2 norm of the previous step minus 2 tau times this. Or maybe I just want an inequality. Or maybe I don't exactly know what to put here because I'm in discrete time, so should I put k or k plus 1 here? This kind of inequalities I'm considering. So a very first example of a quantity that of which I can study the evolution in time is the function f itself, because of course f decreases both in the continuous in time evolution and in the discrete. And in this case, you're also interested in proving, in finding the rate of dissipation of this quantity. And what is easy to do is that rho k plus 1 gives a better result than rho k, so you decrease at least by distance square divided by 2 tau. And if you use the fact that the distance square as the L2 norm of the displacement, which is grad phi, but grad phi is tau times the gradient of the first variation, then you get this quantity, which is essentially sort of Fisher information. And this is exactly the quantity that you get if you differentiate in time the f over the equation. The problem is that here you have a factor 1/2, which I don't have here. Why? Just because this estimate was not optimal. In this estimate, I only use the fact that rho k plus 1 is better than rho k, and not the fact that it is the optimizer. So two possible ideas on how to improve this, having in mind the functional f and maybe some other extensions. The first one concerning f is the idea by De Giorgi about the variational interpolation. That is, try to exploit how much the rho k plus 1 is better than rho k. And you can do it by an interpolation in time, where you define some auxiliary variational problem with a parameter, which is not tau, but it's something between 0 and tau. You get a curve of optimizers, which interpolate between rho k and rho k plus 1. And what you can prove is that how much you're better than rho k is given by the integral in time of this term as sort of Fisher information of the interpolation. And at the limit when tau goes to 0, having the Fisher information of rho k plus 1, or intermediate interpolation, it will be the same. So this is a way which works for the function left. Another technique could be something which is based on this flow interchange technique that I explain in the next slide, which is more general, because it does not concern only f. You take another functional g, and you wonder how much g decreases along the iteration of the gradient flow of f. So the inequality that you get is this one, if you assume that g is geodesically convex in the Western space. Two possible. What is interesting is that this rate is exactly the one that you get in the continuous equation. You differentiate g, and you get dg over d rho times the time derivative of rho, which is the divergence of this. So this is exactly sharp. How can you get these? Two possible ideas for the proof. The first one is the original one in the original paper. Is exploits the geodesic convexity in terms of the time derivative of the distance squared to a fixed point along the gradient flow of g. That's why it is called flow interchange. You take the rho k plus 1, which optimizes one step of jko, and you start from it a gradient flow for g. It's a family of perturbation of your optimizer, because you're starting from an optimizer curve, and you differentiate in time what happens to the quantity that you minimize. So you look at the quantities you're minimizing, and its derivative at time 0 should be positive. What happens is that you know an information about this derivative along the gradient flow of g, and then you compute this one, and you get this term, and you get the inequality. This is a possible proof. Another possible proof, it's slightly different. You take a curve which is a geodesic connecting the optimizer to the previous point. And you use the fact that if a function is geodesically convex, the value at the end minus the value at the beginning is larger than the derivative at the beginning. And that's the point where you use geodesic convex. And then you compute these derivatives. And you have to exploit the fact that the velocity field of the geodesic, the initial velocity field, is minus grad phi, because you go from identity to identity minus grad phi. And then grad phi is related to this one. So this in many cases, these two gradients have the same sign. For instance, imagine that you have as an energy an integral of a function of rho, both for f and for g. So in many cases, this is positive. For instance, this could be gradient of f prime of rho, and this could be gradient of g prime of rho, and f and g are convex. So you can prove that this functional g decreases. For instance, if you apply to the LP norm, you can prove in some cases that all the LP norms decrease, which also implies if you take p to infinity that the L infinity norm decreases. This works for upper bounds, an infinity norm in the upper sense, because unfortunately, negative powers are not geodesically convex in general. So if I want, and then I change the technique, if I want to say something about upper and lower bounds of the densities, then I will do something different. I will use, for instance, the Monge-Ampère equation that Alessio introduced in his talk, and that I will write in terms of the transport, which is identity minus grad phi. So here, instead of a determinant of an Hessian, I have a determinant of identity minus the Hessian. Here I have g of t of x, and here I have rho. You don't have to worry about in which sense this equation is satisfied, because suppose for a while that g is infinity, then prove with the optimality conditions, which are something like f prime of x rho plus phi equals c. So f prime of x rho is the same regularity as phi. And phi is typically at least a Lipschitz function. So immediately you get, in a way which depends on tau, that your rho is Lipschitz. C is infinity, then you apply regularity results that Alessio mentioned to obtain that if you transport a C0 alpha density to a C0 alpha density, then you are C2 alpha. You didn't exactly mention this one, I guess, because you just said that you are C infinity. But so immediately it means that phi is C2 alpha. But if phi is C2 alpha, then rho is better. And if rho is better, then phi is better. You can say that for a fixed step, if you start from G infinity, everything is infinity. So this equation is satisfied in a very classical sense. And now, suppose that your function is this one, and I consider a maximum point for the first variation, which is typically something which includes a function of rho. In the Fokker-Planck case, it is log rho plus v. I take a maximum point for log rho plus v. If it maximizes this, then it minimizes phi, because the sum is constant. If it minimizes phi, the gradient is 0 and the Hessian is positive. But then in this determinant is less than 1. So the value of rho is smaller than the value of g in the same point, because gradient is 0. And since f prime is increasing in the rho variable, you get that this f prime of x naught rho x naught is smaller than f prime of x naught g of x naught. But this is equal to the maximum because I take a maximizer, and this is smaller than the maximum. So this quantity decreases along iterations, the max. And you can do the very same with the minimum. It will change the sign. So for instance, if you apply to Fokker-Planck, log rho plus v will have a maximum which decreases in time and the minimum which increases in time, which implies uniform bound along all the iterations for log rho and so for rho, from below and from above. If you apply to other equations, for instance, a porous medium, if you do for a porous medium without the potential v, again, you have a uniform bound from below and from above. From above, in general, it works for every equation. From below, the problem is that maybe a bound on f prime of x rho from below is not enough to get a strictly positive bound on rho. If you don't have this property like in the log, where that log of 0 is minus infinity. So essentially, in order to deduce in general lower bound, you need that your f prime, if you put 0, is very, very small. Minus infinity if possible. Now, in all this proof, in all this slide, of course, I'm cheating because I'm saying, suppose that the point is not on the boundary. So if you do it on the torus, it works. If you do it on the full space, but then there is another problem. It's not clear if the maximizer exists. How can you exclude the boundary? It is possible to exclude the boundary. Maybe I can also do a very short picture. What about grad phi on the boundary? X minus grad phi is the transport. So this is the opposite of grad phi. It means that grad phi must go outwards. So the gradient of phi is directed outwards. It means that the minimum can never be obtained on the boundary, the minimum of phi. So the minimum of phi is not on the boundary, which means that the maximum of something with rho is inside, there is no problem. It's more delicate for the maximum of phi. And then, again, if you suppose that everything is completely smooth, then the transport is a diffeomorphism. So the boundary is sent to the boundary. So if you take a point which maximizes phi, you cannot say that the gradient is 0 because you're on the boundary, but the gradient should be orthogonal to the boundary. So the gradient should be like this. But then the transport will go the other direction, and if it is a diffeomorphism, it sends the boundary onto the boundary, so it has to go either to the same point. If it is the same point, it means that the gradient is 0, and if you have a maximizer on the boundary with the gradient which is 0, you can anyway go on with the analysis, because anyway the Hessian has a sign and so on. Or you go the other side, and this is impossible. You cannot have a monotone diffeomorphism, an optimal transport, which sends, imagining the ball, which sends the North Pole to the South Pole. And more generally, if you send this point somewhere, and you look at the normal here, then you take this normal, and if this normal is an enteric direction here, you get a contradiction. Because where do you send this point? By monotonicity, you should send it outside the domain. So it's a necessary condition that the scalar product of the normal in the starting point and the normal in its image should be positive. So you cannot go the other side of the domain. And so here you can also find a contradiction. By the way, on the ball, it means that the North Pole can only be sent to the North Hemisphere. And we keep in mind this, we'll use it again. So this is some estimates I can prove using Monge-Ampere on rho. What about the gradient? I take the Monge-Ampere equation and I differentiate it once. Now I write it here in coordinates, so I take the log of the Monge-Ampere. Log rho is log of the determinant plus log g. I differentiate. I put a tilde not to write a log rho every time, so rho tilde is log rho and g tilde is log g. And I have this. So the matrix which appears here is the inverse of the identity minus the Hessian, because when you differentiate log of a determinant, you get the inverse of the matrix times the derivative of the matrix. Here it's more complicated than on the left-hand side because G was composed with T, and so you also have the Jacobian of T, which is identity minus the Hessian of phi. So these are the components HI of the identity matrix. Then I multiply times phi I, essentially I get scalar products, grad phi, grad rho tilde, a strange term, and this. And then I take a maximum point for the modulus of the gradient of phi. I suppose that it is not on the boundary, and there are a lot of terms which help me. For instance, this will be 0, first order condition, so this term disappears. And this will have a sign. This is the Hessian of the gradient square. And so this gives me a sign for this term. And so in the end, I get this. Now, rho tilde is almost v, because log rho plus v is minus phi. So I add and subtract v on both sides in order to get some rho tilde plus v and to use rho tilde plus v equals minus phi. I don't do all the computations. I mean, this allows to conclude, but I don't detail all the computations now. But what do? You add grad. I said that you add grad v on both sides, but attention. Here I want to add grad v in the point x, and here I want to add grad v in the point t of x. So I add and subtract the difference, and so I get that this term is more than this one plus an error term which depends on the difference grad of v in a point x minus grad phi minus grad of v in x, and this is grad phi. So just with an assumption on the convexity of v, I can handle this term. And if I suppose so that v is more convex than alpha times the identity, alpha could also be negative, I can control this term. And what I get is that the maximum of the gradient of log rho plus v in the new step is smaller than the previous maximum, times 1 if alpha equals 0, or you have a correction term, which is like 1 plus alpha tau, which means that if alpha is strictly positive, you decrease exponentially. So you can prove that the gradient of log rho plus v tends exponentially to 0 in L infinity norm if your potential is strictly convex, or otherwise you can control. Again, in all this slide, I'm supposing that the maximum is not on the boundary. How can I handle the boundary? Here there is a very algebraic trick which works on the ball. If you are in the ball, use the fact that the boundary is sent to the boundary, and this means that there is a rigidity. You have this quality which is valid everywhere on the boundary. X dot grad phi equals 1/2 grad phi square. But this is the quantity I'm trying to maximize. So you take a maximum point, and you say that you have optimality condition because you maximize, so the gradient should be parallel to the normal. But also, if you look at this quantity, you're not really maximizing this quantity everywhere. You're just maximizing it on the boundary because it is only on the boundary that this coincides with what you want to maximize. So what you get is that the gradient is equal to something times the normal, and then you take scalar products with x, with grad phi, with a suitable constant, and you arrive to a certain inequality, which is the maximum divided by r square should be larger than 1. But this is not possible because you can never move one point to the other hemisphere, which means that the distance from one point to its image is at most square root of 2 times r. And so this is at most r square. And so you find the contradiction. So in the case of the ball, you can guarantee that the grad phi square never attains its maximum on the boundary if everything is smooth. And what about other convex domains? You just take a convex domain and you put it into a large ball, and then you say that it would be the same if I had a potential v, which was what I want on the domain, and plus infinity out of the domain. So putting a potential which is plus infinity out of the domain is the same as imposing that the measure is concentrated on omega. Instead of using a potential which is something and plus infinity, I approximate with something which tends to plus infinity out of omega. And what is important is that in the estimate, the only quantity which is important is the convexity of my potential. So I can take a function which is convex on omega and plus infinity elsewhere and approximate with a sequence of smooth functions which are say equal to my v on omega, and then they tend to plus infinity and they preserve the same convexity. If I had to use the Lipschitz constant of my potential, then this would not work. But if I just need a lower bound on the action, this is okay. And so you can use the result on the ball to deduce a result on every bounded convex domain. So you can obtain this estimate. So now this estimate was done, written in a not very readable way by Paul Lee, just because instead of saying take phi, which is the Kantorovich potential, he wrote everywhere log rho plus v, and you will see in another slide also the C transform was always written as the C transform of log rho plus v instead of using the other Kantorovich potential. So it's a very interesting paper. So this is just a translation of what is written. This computation was done by Lee in the torus. And the contribution that I did with a student is to consider the bounded domains. Now, this is for first order equation. Then Lee, and here I don't claim anything else apart from the fact that I read the paper and it took me some time to understand. Lee also had the computation, again on the torus, for second order derivatives. That is, you can prove that there is a bound which is about the semi-convexity of the log rho plus v, which is preserved along the iteration of the JKO scheme for the Fokker-Planck equation. And what's the key point? You differentiate twice the Monge-Ampère equation. And there are a lot of interesting ideas, because if you differentiate twice and you write this, then you see that you have a term which has a sign, This is based on the fact that log of the determinant of a matrix is a convex function. You have a term which has a sign, and since this term has always the same sign, if you want to obtain something, you cannot choose either to maximize or to minimize. You just have one of the two which works. If you minimize the first eigenvalue of the Hessian, then when you minimize, you have a positive sign. So this is minus positive, and this is also minus positive, and it has they should have the same sign. So you can look for the minimum point of the eigenvalues of the Hessian of phi, which means the maximum eigenvalue for the Hessian of log rho plus v. Unfortunately, the estimate that you get, you have the one about rho, the one about g, you have some error terms, but you see that you have something which is quadratic, because here again there is the phi 1, 1 which will appear and multiply these. Unfortunately, what you get is essentially something which evolves in times like the equation x dot equals x squared. It explodes in finite time. So you can, it's already something interesting. Along the iteration of the JKO scheme, if you have an upper bound on the Hessian, then it becomes worse at the next step, and you can say how much, but unfortunately it does not last forever. If instead you write the Monge-Ampère equation for the other potential, for the other transport, that is, here you put g, here you put rho, and instead of phi you use psi, which is its C transform, then again you can take the minimum of psi 1, 1. Everything works the same. The equation will be more or less similar. There will be some sign which will be changed, in particular the sign of the time derivative, because you will have g here and rho here. So you get something about lambda prime larger than lambda square. But now lambda is negative, because a minimum of a second derivative of a function on the torus is always negative. And the maximum, because if you take the minimum of psi, of the eigenvalues of psi, it means the maximum of the eigenvalues of phi, which means again the minimum of the eigenvalues of log rho plus v. So, and the minimum will be negative. So you get something which evolves with x dot equals x squared. So it increases, but it is negative. And so now this is an estimate which lasts forever, which also can be used in the past, because it means that you explode very fast in the past, and it can also be used to get bounds at each instant of time, knowing that you existed till time 0. This is something done by Lee, and unfortunately not able to generalize to bounded domains, because it's difficult to handle the second order condition on the boundary. So these are the proofs that one can do with the with, let's say, pointwise quantities using Monge-Ampère. So the first thing that we did were integral quantities on rho, pointwise quantities on rho, grad rho, Hessian of rho. What about now integral quantities about the gradient of rho? And here there is a magical tool which is called the 5 gradients inequality. When we first introduced it, it was not called by this name, but now there are many people who use it, and we call it this name. How does it work? You take two densities, rho and g, you take their Kantorovich potentials phi and psi, and you take a convex function h, and then you have that this quantity, grad rho times grad h grad phi plus grad g times grad h grad psi integrated over omega, is always positive if you are in a convex domain. Actually, I can also say more. It is equal to this, and this essentially is just an integration by part. In integration by part, you get that this is equal to this term, and both terms are positive because h is a convex, this is a positive matrix, this is a square, and this is, so if h is radial, this is oriented as grad phi, and grad phi dot n on the boundary is positive for the reason that I said here. And the same will be true for grad psi. So this one is always positive. Now, this has been written in a paper where we did this application that I will detail in a while with the Filippo Santambrogio and Velichkov. And now I know that there are other extensions which are being done. Simone has different proof than what we had, and his proof can be adapted to other situations. He presented them many times, but I think it's still not published. A student of mine published with a different proof than the one by Simone in the extension. The student is Thibaut Caillet, who is here. An extension to the case where the transport cost is not the quadratic one, but let's say the power p. Anyway, here we will stick to the quadratic one. A possible application is the following. Take the JKO for integral of f of rho, f with a convex function, and use h to be the modulus, so that the gradient is the normalized vector. The optimality condition is f prime of rho plus phi over tau equals c, which means that if I look at the L1 norm of the gradient of rho, I can write it as gradient of rho times the gradient normalized. But the direction of gradient of rho and the direction of grad phi are opposite. So this is the same as minus grad rho, grad phi normalized. But grad phi normalized is grad h, grad phi, and I have this term with a minus, so this is smaller than grad g, grad h, grad psi. But grad h, grad psi is a unit vector, so this is smaller than grad g. So you see that the BV norm decreases along iterations of the JKO scheme. This works for any nonlinearity f. So for the porous medium equation, for instance, the BV norm decreases. This was well known for the porous medium equation. It's more delicate if you add a potential V. So it brings nothing more to the knowledge about the porous medium equation. What was interesting is that we introduced it to consider the limit, where here you take a power and you send the power to infinity, and it allows you to give information about the problem where the constraint rho less than 1, what is called the Mesa problem in some limits of porous medium equation. Now, can we do something with a potential? Yes, but we may only managed with Simone to do it in the case of the Fokker-Planck equation. So you choose, instead of the modulus, you choose the power p. You also have to choose some correct scaling in tau. And then, essentially, with very similar computations, which I do not detail, and unfortunately are a little bit less easy than what I did for the BV norm, you can prove that this sort of Fisher information, that is, the integral in terms of rho of the p power of the gradient of log rho plus v, decreases between one step and the other with a possible coefficient. So it decreases if alpha is equal to 0. It decreases with a certain rate if alpha is strictly positive. Otherwise, you control how much it increases. And what is alpha? Is the lower bound for the convexity of V. And these kind of inequalities in the continuous setting are exactly a consequence, a sharp consequence of the Bakry-Emery theory, which says that you have a solution of the Fokker-Planck equation if you look not at rho, but at rho divided by the stationary measure, which means rho times exponential V. And here you see that I have a log rho plus V. You have information about this relative density, rho times exponential V, on how much it behaves in time if you compare the gradient of the evolution time t compared to what happens with the gradient at the very beginning. So you have some exponential rate of decrease. So this is exactly an integral case. So the Bakry-Emery theory is stronger than this. It's pointwise. If you integrate, you exactly get this. In particular, if you take P equals 2, this is an information about the Fisher information along the iteration of the JKO scheme. Why does this analysis only work for Fokker-Planck? The main reason is this. You take the quantity you want to estimate, and you write it as grad log rho plus V dot, and I take once I use log rho plus V, and all the other times, P minus 1, I use phi. Because I'm allowed, by the 5 gradients inequality, I'm allowed to have something which is non-linear in grad phi, but I must be linear in grad rho. And here you see that if here I have the log, rho times gradient of log rho, it is grad rho. And then I can use the 5 gradients inequality. If I have another nonlinearity, here I don't have the log. And so rho times the gradient of the nonlinearity is not anymore grad rho, and I cannot exactly use the 5 gradients inequality. Of course, maybe it is possible to do something similar with some error terms, and I think it is possible, but then one has to be able to handle the error terms. So that's why this estimate only work for the case of the linear equation, essentially, Fokker-Planck. Now, for the case of I2, the Fisher information with exponent 2, I can even say more in the sense that I can come back. Let me come back 2 slides. The remaining terms and use them. I didn't use them so far. I just used that this is positive. But this actually is positive and larger than, let's say, this term. Why do I say that I prefer P equals 2? Because here I have this matrix Hn of H. If H is the power 2, Hn of H is a multiple of the identity. And I don't care at what I put here inside. If H is another power, it becomes more complicated. So I take H the power 2. There was a scaling in tau, if you remember. So the Hn of H will be a multiple of the identity. And what I can get is that, if you suppose for simplicity alpha equals 0, that the Fisher information decreases by a term which is 2 over tau times this trace. And I don't have anymore the Hn of H because it is a multiple of the identity. Now, if rho is bounded, and you can replace phi with log rho plus V. If you ignore the fact that here you have this matrix, and if rho is bounded from below, you get an L2 estimate in time and space of the second derivative of log rho plus V. Because you get the L2 norm in space is bounded by the decrease of E2. So if you sum up in time, you get something which is telescopic, and you get an integral in time and space. Now, the fact that you need to ignore rho in some cases for Fokker-Planck, you can have lower bounds. So that's not a problem. Then the problem is getting rid of this term, identity minus the action of phi minus 1. The fact is that morally, every time that I write phi, morally phi is of order tau, because it is phi over tau equals something over rho. So morally, this is not 1, but it's 1 minus tau. So this is something like 1. And it would be interesting to have either a uniform bound of on the action of phi, or even better, to prove that the action of phi really tends to 0. So to prove something like the limit as tau tends to 0 of the L infinity norm is 0, in which case this will be really 1 minus a small error. And then this could even be used, and that's what I did with another former student of mine, former master student of mine, in order to obtain a strong L2H2 convergence of the sequence obtained by the JKO scheme to the continuous in time solution. How do you do this? Essentially, you exactly write all the equalities given by this. So you don't neglect any term in this inequality. And if you work well, and if you are able to prove that this term tends to 0, then you can see that the L2 norm of this log rho action of log rho plus v on the sequence with tau really tends to the L2 norm of the same quantity with tau equals 0. So you don't only have bounds, but if the L2 norm of something, so if you have something which is bounded in L2, so it admits a subsequence which converges in L2, and the L2 norm exactly converges to the L2 norm of the limit, then you have strong convergence. And so this means that the JKO scheme introduced by Jordan and Rotto, where they said it converges strongly in L1 in space-time, and what is very often used is just weakly, for each time you have weak convergence in vastness, and you can improve a little bit. They said strongly in L1. Actually, it is strongly in L2H2. Of course, under some assumptions. This works. How can you say that, of course, under some assumptions which are probably not sharp at all, how can you say that this tends to 0? Since you know that the gradient tends to 0, for instance, if I apply the Lipschitz estimate, grad log rho plus v was bounded, it means that grad phi is of order tau, because it's grad phi over tau, which is grad log rho plus v. So grad phi is small. If I have a uniform bound on a space which is better than C2, then by interpolation, the action tends to 0. So essentially, what I want is to have a C2 alpha bound on phi. I call it gamma because alpha is already something else. So a C2 gamma bound on phi, and the theory by Monge-Ampère, the Monge-Ampère regularity theory says that if I have a C0 gamma bound on rho, then on all the rho, so on rho and g, that is on all the rho k, then I have a C2 gamma bound on phi. Now, the way that we do in this paper is just to say, if I suppose that my starting measure is in W1P with P larger than dimension, then I apply these bounds, and the W1P is preserved. And W1P implies C0 gamma if P is larger than dimension. It's not sharp. A natural question, and I finish with this, and this is the extra estimate that they promised, is it true that Hölder bounds can be preserved along the iterations? For the Fokker-Planck equation, so it's a very particular case, the answer is again yes. And what's the technique, which I do not detail? You take the maximum point of phi of x minus phi of y over x minus y to the gamma. So it's a maximum point over pairs. You have to prove that it exists. Actually, if phi is moot, there is no reason in choosing x and y which go to the diagonal. And then you have to get rid of the boundary. But if you can do everything, then you have some optimality condition. That is that the gradient will be the same and it will be a certain direction. The Hessian will be a certain inequality. And then using again a Monge-Ampère, you can compare log rho plus v in point x minus log rho plus v at point y, and get that the Hölder semi-norm of log rho plus v at time at the new time times a coefficient which depends on the alpha of the convexity of v, the gamma of the C0 alpha, the C0 gamma, and the tau improves the previous result. And so you can see that, for instance, again, if this beta is alpha, sorry. For instance, again, if the potential is strictly convex, you have an exponential decay of the Hölder norm. And if it is not strictly convex, but it is just semi-convex, you have a uniform bound. So you can get also a propagation of Hölder bounds, and that's an open question if you can get some Hölder or Lipschitz bound for other equations than Fokker-Planck. So that's what I wanted to do. I thank you for the patience because I presented a lot of estimates without giving all the details, even if I think if you look well in the slides, there are all the ingredients to redo all the estimates, but I just wanted to give the idea of what can be done about the JKO scheme. And most of what I presented is about Fokker-Planck, and the idea is that maybe you would like to develop similar estimates for other equations. Sometimes we can find, by chance, some estimates which were not known or not easy to get in the continuous setting. One of the advantages of working with the JKO is that you don't have at all to care about regularity. In the sense there is no regularity in time, and in space you can always suppose that you are infinity, if you want. And so everything is fully justified. You just have to, but on the other hand, you have some nonlinear equations like the Monge-Ampere, and you have to use to manipulate the Monge-Ampere equation. And thank you for your attention.
Many thanks for this very comprehensive seminar. Any questions? Yeah.
Thank you, Filippo. I have one provocative question and one more serious. One is concerning how, so your methods are variational, so in principle you can extend also to non-smooth situation like metric measure spaces. Perhaps in that case could be very useful to have this kind of estimates for JKO in the setting.
That maybe in this case it's not so easy to do it on the continuous equation.
Exactly, and in this case you cannot use the smooth regularity results. And the other question is, can you think in the continuous case the commutative Bakri-Emery or Bakri-Ledoux estimates are very useful to get pointwise estimate. Can you try to imagine something also for the JKO?
So for answer to the first question, I would be really, really glad if these estimates could be used in a setting where they cannot be recovered with the PDE methods, like in the non-smooth, but you're welcome to do it. I don't think I will do it. Other question about the pointwise, for the one of the most classical results in Bakri-Emery is the gradient of PTU is bounded by PTU of the gradient. The problem is that PTU of the gradient, what does it mean in a JKO? That you give as an initial measure the gradient of something. It's not impossible, but it's not natural at all. Now, a modulus of the gradient of a density is not naturally a density, even if, of course, you can scale so that it becomes a probability measure, but it's really, really natural. So it means that the PT semigroup, it's linear. Here, the JKO, even if it approximates a linear equation, loses the linear behavior. So it's not natural at all to do this. But it's true that they would like to obtain something which goes beyond the integral estimates of Bakri-Emery. Bakri-Emery is a powerful theory which provides an information pointwise, and then I only consider the integral in space. This is it's somehow disappointing, but I don't think it's easy to do anything more than this.
Any more questions or provocations? Comments? No. Then let's thank Filippo again.
Thank you.
We resume now. So it's a pleasure to introduce the next speaker, who is Jan Maas from IST Austria, who is going to talk about characterizing gradient flows. Thanks.
Okay, thank you very much, Andrea. Yeah, thanks a lot to the organizers for organizing this nice event and this beautiful series of events. It's really a great pleasure to be back in Pisa after these years, and I think it's a great conference. Okay, so I would like to present a project that I've been doing together with a PhD student at IST, Maurice Brooks. It's just a short paper that we put on arXiv just last month. And sort of the story of this work is actually that it came sort of motivated by a question that came out of my joint work with Eric Carlin, where we were looking at gradient flow formulations for dissipative quantum systems. And there was a particular open question that I will talk about also in this talk that came out of this work. And we tried to work on this with Morris, and at the end of the day, we actually ended up proving something very general. Yeah, I hope it will be of some interest here, and I would like to present it. So what is the? Maybe I can start by stating this very general question that we ended up looking. So suppose you have a smooth manifold M, and your data are the following. So you're giving a vector field, smooth vector fields on the manifold, and you're giving a smooth function. And of course, if you do optimal transport, we all like very much gradient flows. So it's I guess in this audience, it's a very natural question to ask, can I actually view the ODE given by this vector field as a gradient flow of my given function f? So that's the question. So more precisely, does there exist a Riemannian metric G on the manifold such that the ODE given by this vector field is the gradient flow equation for my given function f? Yeah. So in other words, can I write my my vector field in this form? Okay, so that's of course a very general question, and of course in this generality, it's the answer is of course no, because there are some kind of obvious compatibility constraints that these the field x and the function f need to satisfy. Yeah, but this is the goal. So we would like to find necessary and sufficient conditions in terms of x and f. Okay, and as I just said, so there are some obvious necessary conditions. And the first one, which is maybe what you observe immediately, is that actually x and the derivative of f, they should have the same zeros. So if x is equal to 0, then also the derivative of f should be equal to 0, and vice versa, right? Because the Riemannian metric is an invertible matrix locally. Okay, so that's a clear constraint that needs to be satisfied. Then there's another condition which is also kind of obvious, is that once you are at a point where x is not equal to 0, then this quantity, so x hit with the derivative of f, should be negative. Yeah, so this you just see that if you look at this equation and you hit it with the derivative of f, then you get exactly this quantity. And on the right-hand side, you get something which should be negative since G is a positive definite matrix. So this is also an obvious necessary condition, which just corresponds to the fact that if you want to have any chance that your equation is the gradient flow of f, then well, your functional should decrease along the flow, right? So this is just the derivative of your function f along the flow. Okay, so these are sort of two very obvious necessary conditions. And maybe if you're very optimistic, you could ask, well, are these actually sufficient, right? So in other words, so once you know that you have a Lyapunov function, can you actually construct a metric such that you turn this ODE into a gradient flow of your Lyapunov functional? Well, that's actually also too much to hope for. And maybe to illustrate what goes wrong, we look at a concrete example. And that's coming from optimal transport, in particular optimal transport in the discrete setting. So the setup is the following. So you're given the generator of a Markov chain, L, in continuous time, on a finite set X. And you let pi be its unique invariant distribution, which exists by irreducibility. And it's also unique. Well, then it's natural to look at, if you want, the discrete heat flow. So in other words, the Kolmogorov equation, which represents the time evolution of your law of your Markov chain. And it's just this system of ODEs, right? Where you have just the change of mass at x is a sum over all the points y, where you look at sort of the incoming flux and the outgoing flux. Okay, so that's the kind of the discrete heat equation on a graph, if you like. Well, the natural or a natural functional to consider in this context is, of course, the relative entropy or KL divergence given by the usual expression, where the reference measure is your stationary measure. So then it's natural to ask, can you write this equation as the gradient flow of the entropy? And or well, the first thing to observe is that this is indeed a Lyapunov functional without any additional assumptions. So the relative entropy actually is always decreasing. But also there's this discrete JKO theorem that we obtained about 10 years ago, which says the following. So if you assume that your generator is self-adjoint in L2, or in this Markov chain setting, it corresponds to this condition on the transition rates Qxy in the stationary measure pi. This is the so-called detailed balance condition, or the reversibility condition of your Markov chain. So if this is satisfied, then you get what you want. So you can write this Kolmogorov equation as the gradient flow of the relative entropy with respect to some Riemannian metric on the space of probability measures. And in fact, we constructed a very explicit metric, which is a discrete analog of Benemou-Poignet formula. Okay, so this can be done, but you see that there is an additional assumption, namely the self-adjointness. And actually, there is a converse. I mean, I stated this as an equivalence. So this is really necessary and sufficient. So there's a result by Dietert, 2013, who showed that actually this detailed balance condition is really necessary. So this, if you connect this to the previous slides, so you see that here you have an example where actually you have this Lyapunov functional, but turning this into a gradient flow requires an additional assumption, right? So having a gradient flow structure is really something which is stronger than just being a Lyapunov functional. Okay, so maybe let me just give you the proof of this by Dietert of the fact that if you have this gradient flow structure, then you necessarily have the self-adjointness. So how do you do that? Well, so suppose that you can write your system as a gradient flow. So that means that you look at this dual generator at X, and it means that you can write it in this form. So this is the metric, and this is the derivative of the entropy for some metric. So more precisely, you can of course compute the derivative of the entropy, which is log of mu at Y minus log of mu at X. And then what you do is you look at this identity around the stationary point. Yeah. So you take mu to be mu epsilon, which is a small perturbation of your stationary measure of this form, 1 plus epsilon psi times pi, where psi is a function of mean 0 with respect to pi. And then what you do is you differentiate with respect to epsilon. And if you do that, then what happens? Well, L is a linear operator. So on the left hand side you get L star of psi times pi, and on the right hand side, if you do the computation, you get this expression where you have this metric. I dropped the indices by mistake, but they're still upstairs, and the derivative gives you this difference of these psi's. Okay, and then you just do some computation. So you say, well, what is this scalar product, this L2 scalar product of L phi and psi? Well, I put the L star to the other side. So this L star is all with respect to sort of the duality between functions and measures. I plug in the formula that I just found. I plug it in here, and I know that I can actually rewrite it in this form, where I use the fact that this metric G is symmetric, right? Because it's a Riemannian metric, so it's supposed to be symmetric. And now the thing on the right is actually something which is invariant under exchanging phi and psi. So what this just shows is that indeed L is self-adjoint in L2. Yeah, so you see that sort of this computation shows that the necessity of the self-adjointness really comes by sort of locally looking at your metric at the stationary point. Okay, so well, what we were actually looking at in sort of this follow-up project with Eric Carlin was kind of a non-commutative version of these things. So we were interested in so-called quantum Markov semigroups, where the setting is you have a finite-dimensional Hilbert space, and you're not looking at probability measures, but you're looking at density matrices, which are made which are just bounded operators on this finite-dimensional Hilbert space, which are positive and self-adjoint and with trace 1. And so they are sort of the natural generalizations of discrete probability measures, which would correspond to the diagonal matrices. Okay, and then we would like to play the same game. So we look at the generator of what is called a quantum Markov semigroup, which is just a semigroup now sort of on the space of matrices, which is positivity preserving, and it preserves the identity. So in this sense, it's a natural generalization of a Markov semigroup. And let now sigma be its stationary state. So this is now a density matrix, which is invariant under the dual semigroup. Okay, then the natural functional to consider here is the von Neumann relative entropy, which is given by this expression. So the trace of rho log rho minus rho log sigma, which is also just a non-commutative counterpart of what we saw before, where you replace the integral by a trace. And this, of course, natural interpretations also in quantum statistical mechanics. Okay, and then the result actually that we obtained with Eric Carlin and also Alexander Meek proved with Wittgenstein is the following. It looks very similar. So if you have self-adjointness with respect to a suitable weighted scalar product, which is called this GNS scalar product, given by this formula. So you have now this sort of this trace duality, but there's sort of a weighted coming from a stationary distribution. So if you have this self-adjointness, then what is called this Lindblad equation, sort of the dual evolution of your Markov semigroup, is the gradient flow of this quantum relative entropy with respect to some Riemannian metric. And in fact, we constructed a very explicit Riemannian metric, again, sort of inspired by the Benamou-Grenier formulation of optimal transport. Okay, so this, so far so good. This looks very similar to what we had before. And then we were interested in the question, well, is this also sort of necessary and sufficient? And then what we observed with Eric Carlin is the following, is actually that we could prove, well, not quite the equivalence, but something very close to it. So we showed that if you have this gradient flow structure for some Riemannian metric, and you try to mimic Dietert's proof before, then you infer that actually your generator L is self-adjoint, but not with respect to the same scalar product, but with respect to another sort of weighted L2 scalar product in this non-commutative setting, which looks like this. And you see that if all these matrices, sigma A and B, would commute, this would be exactly the same thing, right? But of course, things do not commute necessarily. So this is really a different scalar product. So in some sense, we observed that there was a gap between the necessary and sufficient conditions, because in fact, one can show that these notions of self-adjointness are not equivalent. Yeah? So one of them is stronger than the other. So if you're GNS self-adjoint, then you're DKM self-adjoint, but not vice versa. Yeah, so that's the question. Yeah. So the question, I mean, the observation is that one of these results is not sharp, and the question is which of them. That was what we started to investigate them with Morris. This was our motivation to look at this at this project. And in fact, we will show that this is not sharp, so we could improve this one. So back to the general setting. So if you don't care about this particular application, here we are in the setting of the first slide. You have a smooth manifold. I read it slightly more generally, so I'm now given a vector field and a covector field, x and y. In the previous application, y was the derivative of a function, but it doesn't really matter. Yeah, so in the previous slide, it was finite dimensional. Yeah. In infinite dimensions, it's of course much more subtle. Yeah. Okay, but everything in my talk is on manifolds, finite dimensional manifolds. Okay, and the question is, does there exist this Riemannian metric which satisfies this identity, which identifies x and with y? Okay, well, we've seen that there are these two necessary conditions which we observed already at the very beginning. So they need to have the same zeros. They should agree on the sign if you're sort of outside the set of zeros. But now, I mean, what follows from the previous discussion is that there is a third condition which is also necessary, right? And this you find by sort of differentiating this equation at the critical point. Yeah? So if you differentiate it at a critical point, well, what you get is that you find the derivative of x, and by the product rule, you would get the sort of the derivative of g times y, but we're at a critical point, so y is equal to 0. So all you get at the right-hand side is that you get this g, and then the derivative of y. So this first condition is actually sort of, there should exist a scalar product such that this identity holds, yeah, at every fixed critical point. Okay, and in this particular example, this corresponded to this detailed balance conditions. Okay, then here's the theorem. but need some assumptions. So our assumptions are the following. So we actually assume this kind of regularity. So we assume that X and Y are actually real analytic in a suitable chart around each critical point. And we also assume that on the set of critical points, actually the derivative is non-degenerate. So this guy is invertible for some or equivalently any connection. And then the statement that we have is a complete characterization of the following sort. We show that if these three conditions hold, which were sort of clearly necessary, then you also obtain the existence of a Riemannian metric on the manifold such that this identity holds. So we have a complete characterization. Okay, so that's the main result. So let me make some comments on this. Okay, well, as I already emphasized, sort of the necessity of these three conditions is clear, and what really remains to be done, and it's the non-trivial part, is to construct this metric satisfying this desired identity, assuming that these three conditions holds. Okay, second sort of easy observation is that it's enough to do this locally, right? The problem is completely local. If you can do this in the neighborhood of every point, then you can just paste things together using a partition of unity. So it's really a local problem. And in addition, so this is absolutely, I mean, very easy at every point, which is not a critical point. Yeah, so where these fields X and Y are non-zero. Because why is it easy? Well, the only thing that you require is basically you're looking for a positive definite matrix which maps one given vector to another given vector, right? And you want to do it in a smooth way, but this is not a problem. So here is one way to do it explicitly. So what you can do, for instance, if you have a guy in the tangent space, you can actually decompose it in such a way that you have one component of Z, which is sort of a multiple of X, and sort of the other component actually annihilates Y, right? And you find a unique decomposition of Z at every non-critical point, where X and Y are not equal to 0. And then the way how you can construct a metric explicitly is by this very simple formula. And basically what it says is the following. So you can do whatever you want on this part, which is sort of the part which annihilates Y. And you have to do something very specific on this one-dimensional direction. So this is what happens in this one-dimensional direction, where you just you give it the right values. And on the other part, you can just use any background metric that you want. So this can, for instance, be found in a paper by Bartachil and Pasangova. And this defines a formula which is well defined on the whole manifold, except at the set of critical points, and it satisfies the desired identity. Yeah. What's the question? Yeah, so this is by notation for so it's parallel to X. So it's not really an orthogonal decomposition, but there's sort of a direct sum. Yes, there should be some. Yes, this should be a parallel. Exactly. Yeah, thank you. Yeah, sorry. Good point. Okay, so that's what happens outside a set of critical points, and the non-trivial part is actually to construct this metric sort of in a smooth neighborhood of a critical point, yeah, or in a neighborhood of a critical point in a smooth way, and that's not obvious. And just as a remark, that if you would just look at this formula, then in general, I mean, this does not extend smoothly to the set of critical points, even in very simple examples. So, for instance, if you're in R2, say in a small neighborhood of the origin, and you take these vector fields X and Y, which are just the identity, and if you take as your background metric something given by this form, so some small perturbation of the identity matrix, and if you just look at this formula, then you find that this extends continuously to the origin, but it does not extend in a continuously differentiable way. So it's not C1. So this shows that it's really kind of constructions like this will not give you the smoothness in a neighborhood of a critical point. Okay, so how do we do it? So how do we actually construct this metric around the critical points? The answer is the following. So we suppose that the metric that we're looking for can actually be written in a power series expansion, like this. And I'm also working now locally in a chart, which I can do. Yeah, of course, the problem is I need to find these coefficients, and I need to show that whatever expansion I construct actually converges. So here's how you end up with the coefficient. So you do the natural thing. So you suppose that you have this identity that you're looking for, and then you start actually differentiating. So if you differentiate this identity once, well, you get the following. So you get the derivative of x, and you get two terms on the right-hand side. But yeah, as mentioned before, if you look at it at a critical point, then this term is going to be 0. So this vanishes, and you only end up with this. And the existence of a scalar product G satisfying this identity, that's what's the assumption, right? That's the additional assumption that we had to put in as a further assumption. Okay, and then you continue. So you start computing second derivatives. Like this, in two directions, you get a bunch of terms. Again, one of them is going to cancel because you're at a critical point, and then you get a relation between the first and second derivatives. Yeah, so in other words, what this identity says is that these first order derivatives, which are tensors of this form, they satisfy this tensor identity, where u is given in terms of the derivative of y, and r, the right-hand side, is given in terms of derivatives of x and derivatives of y and the guy that we knew from the previous step. So this is an equation that these derivatives are supposed to satisfy. And then the lemma that we show is that actually you can solve these equations. So you can find a solution to these tensor equations with the right symmetry conditions. Okay, and then you can go on, right? So this of course gives you a candidate to the first order terms in your Taylor expansion. But you just go on. So you compute actually now partial derivatives of arbitrary order, and you find again that they should satisfy some system of equations for certain tensors. Here I use this head notation that you sort of remove one of the indices. The particular form of the equations is not super relevant now, but you get sort of a generalization of what we saw before. Where R is also a given tensor in terms of derivatives of x and y, and sort of guys that you knew from the previous steps. And then the lemma says that you can also solve this tensor equation, and it also has the right symmetry conditions. So that is something that you need to do. Okay, and once you solve these equations for these tensors, then you're in business, because now you can sort of do what you want. So you can actually construct this power series. So the zeroth order term is the scalar products, which sort of you assume to exist by assumption. Then you sort of iteratively solve these tensor equations, which we can do by the previous lemmas. So this gives you these coefficients t, where are they written? Well, these coefficients t with many indices. And then you expansion in this way. And this is, of course, a candidate for your metric. And then what you need to do is you need to show that this power series actually, of course, converge in a suitable small neighborhood of your critical point. And you need to show that it satisfies the desired equation. So that's what we do. So we show the convergence in a small neighborhood, and we show that it satisfies the desired equation. And here, of course, the assumption of real analyticity of the vector fields is important because we use all the derivatives of x and y in this construction, and we also use the fact that they satisfy suitable bounds to really ensure the convergence of this power series. Okay, so that's very briefly kind of the sketch of the structure of this result. I guess it's natural also to ask yourself whether you can actually weaken a little bit this regularity. So can one do something without this real analyticity assumption? The answer is yes. So here's a result which is very similar to the main result, but with different regularity assumptions. So k is now an integer, and I should say that case k equals 0 was treated before in a paper by Billy. And you assume the same as before, but now x and y are of class ck plus 1 in some chart around the critical points. We still have the non-degeneracy condition, and then the statement says that if you have these three necessary conditions, you can construct a Riemannian metric, but it's not necessarily smooth anymore, so it's of class ck. So you lose 1 degree of regularity. Okay, and how do you do this? Well, the proof idea is actually you used the ideas from the previous proof. So again, you're going to solve these tensor equations for the derivatives, but now you cannot do it for arbitrarily large values of n because these derivatives do no longer exist. But you can do it only for n up to k. But this you can still do. And then what you do is you define this background metric just by this Taylor series, where the coefficients are exactly sort of these tensors t that you get from the tensor equations, but it's a truncated power series, right? So you stop at degree k. And then what you do is you use actually this construction that we saw before. You look at this perturbed metric, where actually you put as a background metric now this particular sort of well-chosen metric, and you use it. You look at this rank 1 perturbation, and this metric actually now does the job, and it has also the required regularity. Of course, that still requires a proof to show that this really gives you something which is of class ck, but this can be done. Okay, so I think that's kind of the general part, and now let me just come back to sort of our motivation, so we can now sort of also answer the question that we had with Eric as a kind of direct corollary of this general result. So if you have a generator of a quantum Markov semigroup on a finite dimensional Hilbert space, then the following conditions are equivalent. So you have the self-adjointness with respect to this so-called BKM scalar product, given by this formula that we saw before. And this is equivalent to the existence of the gradient flow structure for the entropy. So this is sort of a weaker condition than that we had before, and this follows immediately from this general construction. So I should say that under the stronger assumption of this so-called GNS symmetry, we constructed this explicit kind of transport distance based on this Benamou-Bonnier formula, which is a very nice structure, and which we can actually also exploit to say interesting things about certain quantum Markov semigroups. So we can study geodesic convexity and obtain some results in some applications. Of course, the construction for these more general class of semigroups, I mean, it still gives us a metric, but it's it's very much non-explicit, and it's not completely clear whether this metric is also useful in applications, but at least sort of this result shows that it exists, and that there's this class of Markov semigroups where I think it's worth investigating further, whether there's also sort of a particularly nice metric which you can actually really use to do some analysis. Okay, with that I would like to close, and thank you very much for your attention.
Thank you, Jan. Any questions? Comments? Yeah.
So, I thank you for your talk. I'm just trying to understand the level of explicitness of the construction of the Riemannian metric. So, are there examples where you had where you were able to say you start with the manifold and the functional, and then you were able to explicitly write down the relevant metric structure, like in a case where it was not known before, or?
Well, no, I mean, I think in this generality, it's not explicit, right? So it's really a local construction, which is also not unique, but we construct some metrics sort of locally in the neighborhood of the stationary point, and then you paste things together using partition of unity.
So you'd have no explicit.
No, so it's not at all explicit. Yeah, I think in this generality maybe it's not realistic to expect any explicit formulas. Yeah. Of course, in application, you're often interested in, I mean, you want to have a good Riemannian metric, right? Or which you can do some useful analysis. I mean, in this sense, this result doesn't help you, but at least it helps you to rule out cases where actually you cannot hope for gradient flow structures in some sense. Yeah.
I see. But I guess if you had an explicit enough atlas, like if you have some manifold that has a nice atlas that only has like one chart or something, would you be able to write it down explicitly, or?
Not really. No, I think that doesn't really simplify things. So even if we do them, you know, in Euclidean space or so, we would still end up doing similar arguments. So that doesn't simplify.
Okay, thanks.
Actually, on a similar note, once you have this existence of one of them, right? So can you ask for the best one in some sense? So you do some kind of optimization procedure for, is there a way of selecting the best ones? Of course, in quite generalities, I mean, it maybe does not have any meaning, but you know, for special cases where you expect some structure, let's say I want to have that, then the Ricci curvature is something which is nice or something like that. Can you exploit? Do you expect something like that to be?
Yeah, I think that's an interesting question. I don't know. I mean, you're right, of course, that there's lots of non-uniqueness in the all construction, right? And you can, you know, especially in these non-critical points, you can just do, you know, make some perturbation in one direction and still keep the gradient flow structure. So yeah, I don't know. I don't know I mean, I wouldn't know how to formulate sort of this kind of optimality condition or minimality or so. Yeah, I mean, even for like something like Wasserstein gradient flows, right? I mean, I think everybody would agree that sort of the Wasserstein metric is the natural metric, but of course you can also perturb it in some silly way and you would still preserve the gradient flow structure. I don't even know for let's say Wasserstein whether there's any statement which says that this is really, you know, the minimal or the optimal or the best. Yeah.
Any more questions? One, just a curiosity. So is the motivation coming from the finite-dimensional Hilbert spaces, or the long-term goal is to go to infinite-dimensional Hilbert spaces? And how far is that, if it's the long-term goal? Yeah.
I mean, that's of course also a good point. You mean particularly about these quantum Markov semigroups, you mean? Right? Yeah, that's right. So of course, I mean, if you want to do quantum mechanics, you want to do it in infinite dimensions. So that's definitely something which is important and interesting, and there have been developments in this direction. So, for instance, Melchior Weert, who is a postdoc at IST, has a very nice work on extending these gradient flow structures to some classes, at least of infinite dimensional quantum Markov semigroups. But I would say the full picture is not yet there. On the other hand, I think, you know, for many applications, it's enough to be able to work with finite dimensional Hilbert spaces, and sort of as long as you get bounds which are sort of independent of the dimension. Yeah, and you know, in many examples, sort of the essential technicalities are already there in finite dimensional problems. But you're right. I mean, it would be very desirable to have a full theory also in infinite dimensions.
Okay, there are no more questions. Let's thank Jan and all the speakers of the morning. And we resume tomorrow, and I wish everyone a good afternoon. Any particular... No. Okay, see you tomorrow.